Hello students, welcome to Marine Edge. Your IMU-CET is almost on your head, and through this lecture we'll be covering each of the upcoming chapters that will be coming for your exams through mind maps for a quick revision. So without any further ado, let's get started. So units and dimensions, if we discuss about whether how many questions were there from this chapter from the previous year, there were almost one or two questions that will be coming each year from these topics, including errors and all of that. So, but this units and dimensions is the base of your physics, right? This is the basic concepts, the units, the formulas. So let's get started on that. So first of all, we'll talk about system of units. We have SI units, we have CGS unit, we have FPS and MKS units, right? As mentioned here. So SI unit is the standard unit that we have been using throughout everywhere. And in SI, other than that, they're also going to measure smaller quantities. We use centimeter, gram, seconds unit. FPS and MKS were two different sets of unit that was developed across the world. Since all these units were, when people were developing, different parts of the world started using different units, right? So, for example, UK uses this FPS and normally we use MKS units, right? Now, let's move forward. So, what are dimensions? So whenever we are expressing any of the base quantities, we express them in the terms of dimensions. So what are the basic dimensions? We have mass, length, time, current, temperature, and mole. So these are the seven fundamental quantities, and we express that using these dimensions. Now we also have other quantities, like when we talk about length and talk about time. From length and time, we also have velocity. Velocity has also has a SI unit, that will be your meter per second, right? But those are derived quantities. Those quantities can be obtained using these seven fundamental quantities. So we have fundamental quantities, which are 7 in count, and for each of the quantity we have their own SI unit. That length is meter, mass is kg, time is seconds, temperature is Kelvin, current is ampere, and amount of substance can be measured in mole or candela. And these have been crossed. This should be candela and there should be mole, okay? And luminosity in candela. Now, all the other quantities that we have, velocity, acceleration, force, energy, these are all derived quantities, all right? Now, moving forward, we have error. And so what is error? So whenever you're measuring something, you cannot exactly always be right. Sometimes this error can be because of manual issues or your observation skills. Sometimes it is because the device or the measuring unit that you're using itself is flawed. So we have different types of error. We have absolute error, we have relative error, percentage error. Now, before we move forward, let's discuss these three. Absolute error will be what? So let's say you measured gravity. So you measure gravity using that pendulum experiment we have, right? So we know that the value of gravity is 9.8. But after 5 examples or 5 experiments, your each value was 9.7, 10.1, 9, 9.8. So absolute error will be the difference between the true value, that is 9.8, and the measured value that you are calculating. Relative error is absolute error divided by true value. Percentage error, that is the percentage of error that you received. Relative error into 100. Instrumental error, it comes because of faulty instruments, right? Sometimes, let's say, your measuring scales, instead of starting from 0, it is marked starting from 1. Least count error, the minimum value. So least count is the smallest unit that you can measure using any particular instrument. Observational error, human mistake, or environmental or temperature factors. So like in greater humidity, the oscillation will stop faster. So these factors also determine your errors, okay? Now, we also have supplementary SI units. So apart from fundamental units and derived units, we also have supplementary units that are plane angle and solid angle. Now, plane angle is used to measure the angle of any particular 2D angle, okay? And solid angles, when we have a solid cone structure, the angle inside this cone, this is called a solid angle, and they are measured in radian and steradian respectively. Now, what are the applications of having dimensions? So, dimensions follow the principle of homogeneity. What does that mean? We can only add the quantities that are having similar or equal SI unit. So for example, you cannot add 5 meter and 10 centimeter, or you cannot add 5 meters and 10 kgs. Okay. Now moving forward, we have conversion of units. So you can easily convert one unit of a particular, like for example, about length, you can convert a length from meter to centimeter to millimeter in different quantities. So as you convert meter to centimeter, what will happen? As the size of the unit becomes smaller, the numerical value starts to increase. Okay. And We use dimensions to derive relationship between different equations. Okay, so these are the three uses of dimensions or applications of dimensions. Next, we have order or magnitude. Now, for example, when we're trying to describe something of a larger size, for example, let's say speed of light. So we measure it, we write it as 3 into 10 to the power 8, correct? Now, this 8 is the order of this magnitude. Okay. Now, and whenever we are talking about any particular unit, for example, if we're talking about force or if any particular object or any particular dimensions, any particular measure, so we can write it in dimensions. So any of the vector or any of the values that we will be having can be represented using these 7 dimensions. All right. So for example, in your exams, you will be always seeing questions like what will be the dimension of Planck's constant, what is the dimension of the G or gravity, what is the dimension of constant G, the capital G, when we talk about the calculating the force between two objects. So multiple values. So each of these dimensions can be mentioned using these 7 symbols. Length is denoted by m, mass also. Length is denoted by L, sorry. Mass by m, time by T, temperature by K, electric current by I, amount of substance by mole, and luminosity by CD, as we discussed before. Now, moving on, next we have errors in measurement. See, so when we talk about errors in measurement, let's say you have the values of a rectangle. Okay, we have the length given, breadth given to us, we have the length given to us. If we have to calculate perimeter, the formula will be 2L plus B. So now when we talk about addition or subtraction of errors, so what happens here is the error tells you that, okay, if I'm saying that the length of this rectangle is, let's say, 50 centimeter, but I might be 5 mm, but the actual measurement might be 5 mm extra or 5 mm less. So this is the error in my calculation, that is delta A. So what is error? Measurement containing some uncertainty with which we are calculating. Accuracy means how close to the measurement of the true value we are. Okay. Precision is what is the resolution or limit to the quantity that is being measured, how precise or how absolutely correct I am. Okay. Then absolute error, that is the difference between the individual measurement and the true value. And the least count is the smallest value that can be measured using whatever scale we are using, right? As we discussed before. Now, when we talk about, so if I have been given this rectangle and I have to calculate the perimeter. So the formula for perimeter will be what? 2L plus B. So we are adding two values, right? A and B. And I'm saying there's a 5 mm error in the calculation of length and 2 mm error in calculation of breadth. So when I'll be calculating the perimeter of this particular rectangle, the error will be added. Okay, we add the error. Similarly, if we are measuring some quantity where we subtract the 2 units, in that case also the error is added. Okay. Now moving forward, when we have to divide or multiply the value, for example, if we are calculating the area of the same rectangle, so the formula for area will be what? L cross B. Right? So when we are talking about area, in that case, we calculate the percentage error or fractional error. That is, we divide the delta A or the error with the actual value of A plus delta B with the actual value of B, like this. And similarly, the same formula goes for division as well. Now, power rule, when we talk about some error that is having some multiplication that is having power. So A raised to the power P, B raised to the power Q, C raised to the power C, and D raised to the power T. In that case, when we'll be calculating error, in that case also we'll be calculating fractional error. Okay, first of all, fractional error is what? Error divided by the absolute value. Okay, that is called as the fractional error. All right, now, so when we have exponential power, this power is multiplied before the fraction of the error. All right. Now, next we have percentage error, like we saw before, absolute error divided by whatever the initial or the whole measurement is into 100. This fractional error is also called as your relative error. All right. Now, rules for determining number of significant figures. So when we talk about significant figures, those are the number of values in your given outcome or calculation that will tell you the precision or how accurate your calculation is. Okay. Now, for example, for the numbers with no indicated decimal, for example, if we have 973000, okay, this number has no decimal count. So all non-zero digits are to be counted as significant. These three will be counted as significant. The terminal or trailing zeros are non-significant. These three will not be significant. Now, when we have decimal values indicated in the number, so all in the same case, same value, all non-zeros will be counted as significance. Zero that have any non-zero digit anywhere to the left of them are considered significant zeros. For example, if I'm writing 0.00027. So these three zeros here, since these are being followed by numbers, these will be counted as significant. Okay. All zeros that are not covered in the rule 2 are not considered significant. So if there is zeros behind, they are not considered significant. Okay. Now, moving on. Next, we have the measuring unit vernier caliper and screw gauge. So, vernier caliper, we use this device to measure precisely very small height, length, breadth. Okay. And similarly, screw gauge is also a device which is used to have precise calculation of small, let's say you have a very thin wire or a very thin rod. To calculate the diameter of this rod, we will be using a screw gauge. Okay. Now, in vernier caliper, we have the main scale. This is the main scale, and the main scale, smallest unit that can be measured on this main scale is 1 mm. Similarly, in the vernier caliper, this divisions, they are 0.9 mm. And the length, or whatever the value you will be calculating, will be main scale reading plus least count of vernier caliper into VS, or vernier scale division, coinciding with MS. Now, you can just least count of vernier caliper can be calculated as main scale division minus the vernier scale division. Okay. Now, in this case also, you will be having the zero error that is subtracted from the reading. So initially, whatever is these two values are coinciding, right? So, but in case if the vernier caliper has some issues, let's say the main scale initially 0 is coinciding with this one, so that zero error will have to be removed. Positive zero error. If nothing is placed and the zero of vernier scale is to the right of 0. This we are talking about whether the zero error can be positive or negative. So if we have nothing placed inside it, still if this 0 is coinciding with this one, this will be called as a positive zero error. Similarly, if the 0 is to the left of it, right? In that case, we'll be getting a negative zero error. Next, we have screw gauge. Now, what is a screw gauge? This is used, like we discussed, this is used to measure the small diameters through a precise value. Now, the distance between two consecutive threads of the screw, these two screw, that will be your least count, which divided by number of divisions on the circular scale, this scale. Okay. Now, readings will be calculated as main scale division. This is your main scale plus circular scale count. And the corrected value will be reading minus whatever zero error that was initially there. Same concept here also, positive zero error can be there and negative zero error can be there. Alright. Now, next is scientific notation, like we discussed before. So whenever we are trying to write a larger value or a very small value, whichever it is, let's say, for example, what is the value of what is the charge carried by one electron? That is 1.6 into 10 to the power minus 19, right? So this minus 19, that is your notation here, B. And when this value, this can have only one decimal ahead of it. Okay, that is how we use scientific notations. All right. So the final result should retain when we perform arithmetic operation on any of the two elements, any of the two values. Okay, so we ensure that after multiplication, the number of significant figures remain the same. In case of addition also, we ensure, so the final result should be retaining just as many significant figures as there are in the original number. Okay, so let's say if this number has two significant figures, whereas the second number has 00026. Here we have 4 significant figures. So when we multiply it, the outcome, when we note it down, we will only have 2 significant figures. Okay, so here we have 4, here we have 2, but after multiplication, the result should have the least number of significant figure as between the two values. Similarly, when we talk about addition or subtraction, the final results will retain as many decimal places as there are in the original number. Correct? Now, rules for determining the number of significant figures. All non-zero should be counted. Zeros, when we're talking about decimal, in that case, all non-zero numbers should be counted, and the same is the case without decimal. Next, zeros having non-zero anywhere to the left of them are considered significant. Okay, this is only for the case of decimal. In non-decimal, trailing zeros are not significant. Okay, now if we are talking about this, there is no decimal here, but these 3 zeros are significant. Why? Because they are between two numerical values, two values between 1 and 9, but 79 and 30, this is not significant. Okay, so trailing or terminal zeros are not significant, but the zeros between two numbers are significant. Now, All other zeros not covered in the second rule are not significant. So these are the three basic concepts about determining the number of significant figures. Now, next we have vectors. So let's get started on vectors. See, the vectors are a very important concept because this is the basis of whatever further you will be calculating. Vectors are like addition and subtraction for physics. Okay, so let's get started on that. So two vectors are said to be equal only if they have same magnitude and same direction. So vectors are the quantities which have magnitude as well as directions. All right. Now, angle between two vectors, it can only range from 0 to 180 degrees, right? So we have parallel vectors and anti-parallel vectors. What are the parallel vectors? Which have same direction, same angle, and angle between the vectors is 0. Anti-parallel, opposite directions, and angle between them is 180 degrees. Now, whenever we talk about vectors and vector addition, we use the triangle rule of addition. So we have vector A and vector B. See, notice this, the edge or the big end of the vector A, beginning of the vector A coincides with the end of the vector B. So A plus B will always result in vector C. This is the vector rule of addition. Okay. Similar to that, we have polygon rule of vector addition. Multiple vectors, vector A, vector B. So what happens here is vector A1 plus A2 will give you a resultant here, R1, and then this R1 plus A3 will give you a resultant here, R2, and this R2 plus A4 will give you a final result. So this is the polygon law of vector addition. Alright. Now moving forward, we have two types of vector products are there, scalar product and vector product. Now scalars only have magnitude. So when we do scalar product, we use the formula AB cos theta, and this will only result in magnitude. For example, work is a scalar product, that is F dot S. Even if F force is a vector quantity and S direction or distance is also a vector quantity, but when we take dot product, the resultant is always only a scalar without any direction. It just has the magnitude. Next, we have the dot products. Next, we have the cross products. Okay, we'll discuss that later, but first only let's cover scalar products. So this is the scalar products. In scalar product, what happens? I and I. So we have, when we talk about vectors, we have three values, right? I, j, and k. So I dot I is always equals to 1. J dot j is 1. K dot k is 1. Any other value, whenever you multiply I with j, j with k with I, it will always result in 0. Okay. And the angle between two vectors, if you have the scalar product answer, then you can calculate cos theta is equals to A dot B by the magnitude of the vectors. Alright. Now, what is 0 vector? So when we subtract a vector A from itself, we get the 0 vector. Alright. Next, unit vector. So unit vectors only has direction. It has the magnitude of the unit vector is 1. It only has direction. So for example, if you have a vector A as 2i cap plus 3j cap plus 4k cap, it will be pointing somewhere, let's say like this. Now, when we talk about unit vector will have the same direction as this vector. Okay, but the magnitude of that vector will always be 1. That is what the unit vector is. Now, for example, we have I cap, j cap, k cap. That also can be taken as using these we calculate the unit vectors. Now, and in the opposite direction we have minus I cap, minus j cap, minus k cap. I hope that part is clear to all of you. Anyway, next, multiplication of vectors with real number. So when we multiply any given vector, let's say we have to multiply 2i cap plus 3j cap plus 4k cap by 2. We just multiply like 4i, the resultant will be 4i cap plus 6j cap plus 8k cap. That's it. Nothing else is there. Okay. Now, next we have parallelogram rule of addition. Now, what does that mean? So let's say we have this vector A and vector B. The ends of the both vectors are here. So in that case, the resultant vector R. So we draw parallel lines, a line parallel to B and a line parallel to A, and the diagonal will be the resultant vector. And how do we calculate it? A square plus B square plus 2AB cos theta. That's it. Okay. This is the formula. In subtraction, the same plus will become minus 2AB cos theta, and that's about it. Alright. Now, displacement of a vector. So just when we calculate initial, let's say the initial vector range was R1 and the final vector Ri, and the final vector range was Rf. So the difference between them will be given you a resultant of the displacement vector. Alright. One of the very most important concept when we talk about vectors is resolution of a vector. So whenever we have a vector R, it can be resolved into two parts, horizontal component and the vertical component. The horizontal component is always marked as Rx and the vertical component is marked as Ry. Now, so Rx and see, theta is the angle the vector makes with x-axis. And whenever we talk about what will be the horizontal component or what will be the vertical component, let's say it is making a value phi with the y-axis. So the angle that is being shared by the base and the vector is always you taking cos. So here we can write it as resultant will be r cos theta, because the theta is being shared by x-axis and the vector. So r cos theta in x direction and r sin theta in y direction. Similarly, we can also write it as r cos theta, r cos phi j cap, because phi is the angle being shared by resultant and the horizontal line, plus r sin phi I cap, because phi is not the angle being shared by resultant and x-axis. So cos always goes with the line with which the angle is being subtained. Okay, so this is the resultant vector, and you multiply these two values, you'll get your actual vector. So r square x square, because sin square theta and cos square theta will be resulting in 1, so you get your resultant out of it. Now, if you take the ratio of y and x, you'll get your tan theta, or the angle here. Okay. Next, moving on, representation of a vector in 3D. So this is how we represent it. We have rx, ry, rz. This is how it looks like. This will be a point. Okay. And when we mention a vector, it means that it covers rx distance along x-axis, ry distance along y-axis, and rz distance along z-axis. And the value that comes here, that is your vector. Okay. Moving forward, kinematics has been one of the most important one of the most significant chapters for your IMU-CET exam, because a lot of questions has been asked. Even in the previous year, there were 3 to 4 questions asked from this particular chapter. All right, so let's get started on that. Now, for some of the basic concepts that you need to be knowing before going through is the first is slope. Now, whenever we have a line that is making some angle, this angle made by the line with x-axis is called the slope of the line. Okay. So slope is equals to tan theta. For example, this is the line y is equals to mx plus c. For that, theta, or the angle made by the line with x-axis, is called the slope. Okay. Now, next, some basic concepts of integration and differentiation you should be aware of. I hope you have already covered that in maths, but we have a list already provided here. If you can see, these are some basic concepts of multiplication, in differentiation, integration that you will be needing. You don't get a lot of questions with respect to these, but all right. Okay, but just for your basic revision, this is available here. Now, we have 3 major formulas when we talk about solving any question regarding kinematics. That is, v is equals to u plus at, s is ut plus half at square, and v square equals to u square plus 2as. Okay. Now, another, so from this only we can also write s is equals to v plus u upon 2 into t, and s is equals to vt plus minus. Now, these 2 formulas you won't be using very frequently. These 3 suffice for all of your questions. Okay. Next, moving forward, one of the basic understanding that we need to be knowing is, see, from displacement, whenever we have some s displacement, if we differentiate that, you'll get your velocity. And when you differentiate the velocity, you'll get your acceleration. So all the maps, all the graphs that you will be seeing are covered using the same concept. Okay. Now, next very important topic is your motion under gravity. So whenever we throw a ball straight upward, okay, it will reach some maximum height and it will come down. So the 3 questions that are always asked among this is, what is the time of flight, for how much time the ball was in air, that is 2u upon g, h max, or the maximum height it would have reached, u square upon 2g, and what is the time period for going up or coming down. So that is the same, u upon g. While going up, it would have taken u upon g time. While coming down, it would have taken again u upon g time. Okay. So that's why the total time of flight is 2u upon g. Next, we have relative motion. So whenever we are talking about motion with respect to a second, so for example, if a person is walking with 5 meters per second in I direction, forward I direction, another person is walking towards him with 2 meters per second in minus I direction. I mean, he's walking in the opposite direction. How fast will the other person be seeming to come? That is relative motion. If 2 bodies are moving away from each other, towards each other, whatever it is, the motion of the second person with respect to first person, that is relative motion. So the whole concept of relative motion is, we just subtract the motion of the second person by first person. That's it. Okay, velocity can be calculated. So in this case, the velocity, let's say the person A will feel like the other person B is approaching him with the speed of 5 minus, that is 7 meters per second speed. Okay. Now, moving on. Next, we have speed. Okay. Now, average speed is what? Speed or velocity, whenever we talk about it, average means throughout the motion. Okay. So, along the whole time, let's say if you're traveling from a bus, then you took a cab and then you start walking. So, throughout this whole time period, what was the speed? What was the distance covered divided by time? That will give you average speed. Now, instantaneous speed will be what? So, let's say at this point in the bus, your speed was 20 meter per second. When you're traveling alone, it was 5 meter per second. And when you're traveling in a cab, it was 50 meter per second. So at that particular instant, that is called as instantaneous speed. Okay. And the same goes for velocity. Now, the difference between speed and velocity is speed is a scalar quantity, velocity is a vector quantity. Speed comes from distance. Distance is a scalar quantity, whereas velocity comes from displacement, which is vector in nature. Right. Now, moving on. Next, we have projectile motion. Now, we discussed about an object being thrown upward at a 90-degree angle. Now, instead of making a 90-degree angle, if you throw it at some particular angle, theta, in that case, the object will go up to some maximum height and it will come down similarly, but it will make a U-shaped curve or a parabolic curve. This is called as a projectile motion. Now, in a projectile motion, we have another new thing called as range. Range is this distance that is being covered. And range is maximum when the theta at which you are throwing the ball upwards is at a 45-degree angle. Okay. Now, the formula that we needed here is time period for the amount of time the ball was in the air, that is 2u sine theta upon g, or whatever the y component of the velocity was upon g. Then we have the h, the value of h, that is 2y square upon 2g, right? That is the maximum height the ball attained. H is the maximum height. Okay. One second. All right. And finally, we have the range. Range is the whatever distance that was covered by the ball in the horizontal direction. That is u square sine 2 theta upon g. Okay. Now, the path of particle having a constant acceleration. Let's say if a particle is having a constant acceleration, then what kind of path will it be covering? So, now, if the object is having an initial velocity 0, in that case, the object will have a straight line motion. Okay. Now, if the initial velocity is 0 and a is collinear, what does that mean? Collinear means the object will the a is in the same direction as that of the motion of initial velocity. So the velocity vector and the velocity vector and the acceleration vector are in the same direction. So in that case, we also get a path as straight line. Now, next is when initial velocity is 0 and u and a are non-collinear. What does that mean? For example, in the case of projectile motion, u is in this direction, acceleration is in downward direction. So what do we get? Acceleration, that is gravity, is in downward direction and the motion of the object is in some other, let's say some angle theta direction. So we get a parabolic curve. So these are the paths. Okay. Now, if two particles are projected in gravitational field during the same time at the flight of both particles, the trajectory of one particle with respect to other particle will be. So now let's say we are throwing two different objects. Okay. At the same time. So in that case, the trajectory, just for comparison, we can write it as xi cap plus yj cap. Velocity will be what? Differentiate the in position, you will get the velocity, and when you differentiate the velocity, you will get the acceleration. Now, one other thing is the equation of trajectory. This is the formula for equation of trajectory. What does that mean? It tells you the position of x and y. It will take you to xy coordinate of the object or of the ball. Okay. Now, moving on. Next, one of the most common problem that you would have seen with respect to relative motion is the rain man problem. Now, what does that mean? The man is observing rain in a direction of velocity of rain with respect to man. Okay. So first, the concept wise, let's see. There's a man moving with some velocity Vm, and we have rain falling horizontally downward. Okay, in this direction Vr. So in what direction will the man feel the rain is falling? That is called the man's observation of rain with the velocity of rain with respect to man. So Vr, velocity of rain with respect to man. So how do we calculate it? Velocity of rain minus velocity of man. So whatever velocity and direction you will get, you will have to hold an umbrella in that direction to protect yourself. All right. All right, moving forward, we have the riverboat problem, and again, another classic example of relative velocity. So if there is a river, okay, and which is flowing in the horizontal direction, obviously. So now if a boat or a person will be trying to cross this river, okay, moving in the straight x-axis direction, he'll be attaining some drift. So if he's aiming to reach here, instead of reaching here, the person will reach here. That is the drift. Now, so what will be the velocity of boat? We'll write it as velocity of boat with respect to river plus velocity of river. Another classic example of what? Relative motion. Now, moving forward, we have projectile on an inclined plane. Now, instead of throwing this object direct straight upward, we are throwing it on an inclined plane. So, in that case, in the x component of the motion, initially, when talking about horizontal surface, in that case, the gravitation, the value of acceleration was due to only gravity, and that was g. In this case, your gravity will become g sine theta, and in the x-axis component, and in y component, it will become minus g cos theta. Okay, so we have to ensure that when you take the time period, the displacement, the range. So if we ensure these two factors, the formula remains the same. Y component plus the gravitational part. Okay. Now, moving forward, next is friction. So, what is friction? Whatever motion that opposes whatever friction is the contact force. Okay, it tries to oppose your direction of motion. So, if you're trying to move forward, friction will be acting in backward direction. If you try to move backward, friction will be acting in forward direction. So, friction does not oppose motion. Instead, it opposes the relative motion. It only opposes relative motion on the surface. Okay. So, and friction is of two types, static friction and kinetic friction. Now, static friction is the friction that is on an object before the object actually starts moving. So, if let's say you are able to move an object by applying 10 newtons of force. So, until you apply that 10 newton of force, no, the friction force that you will be facing is your static friction. Now, once you have started applying force greater than 10 newton, let's say you start applying 11 newtons of force. Then at that point, after the object will start moving, obviously, because static friction is the friction only in the case when the object is at rest. Now, once the object starts moving, in that case, the friction that is acting on an object is the kinetic friction, and kinetic friction is less than static friction. Okay, so if there is a tendency of relative slipping between the two surfaces in contact, the frictional force acting between them is called static friction. Now, static friction is always higher than kinetic friction. So once the object starts moving, you will see that it is easier to move the object once it is actually moving than to actually make it move initially. Okay, that is because static friction is greater than kinetic friction. And how much static friction is applied? So let's say you are applying, if an object starts moving after applying 10 newtons of force. So before that, if you are applying 9 newton, the friction will also be 9. If you are applying 7 newton, the friction will also be 7. So because of that, you have a straight line curve, okay, making an angle of 45 degrees. Okay, now moving on. Laws of static friction. The maximum value of static friction is limiting friction, okay, and it is directly proportional to normal force acting between the two surfaces. Okay, and what is the force of static friction? Fs, the force is equals to mu, or coefficient of static friction, into normal force. What is normal force? Let's say this is the object and this weighs 10 kg. So it is applying a downward force of 10 kg, 10 newton. Let's say it is of 10 newtons, and it is applying a downward force of 10 newtons. So this, because of this downward force, there will be a reaction force N, that is multiplied with the coefficient of friction to calculate friction. Now, moving on, for kinetic friction, the value of kinetic friction is directly proportional to normal force. Same formula, mu k into N. The same concept is there also, okay. Next, we have circular motion. Now, so before we go there, the first base concept is inertia. So, what is inertia? Inertia is the property or ability of a body to try to maintain or preserve its own state. So, every body, if it is at rest, it will try to stay at rest. If it is constantly in motion, it will try to stay in motion. So, every body preserves its state of rest or of uniform motion in a straight line unless it is compelled to change its state by external force. Okay, and this is called the law of inertia. Now, using the law of inertia, this is the first law of Newton's law. Okay, and from this law only we get the formula for force, that is ma. It is so until there is an external force applied, there will be no change in motion. So if there is no acceleration or there is no force, there will be no change. Okay. Now, the second law, or where we exactly see this F is equals to ma, is this one. So, in words, if you like, the second law states that the rate of change of momentum with respect to time describes force. So, what is rate of change of momentum? Mass into whatever is the final velocity minus the initial velocity. This is the rate of change of, this is change of momentum with respect to time. That is equal to whatever force is there. Now, final velocity minus initial velocity upon time, can we write it as A? So from here we get the formula F is equals to ma. Okay. Now, so let's say we have force F1, F2 acting alongside. So this total force will be equal to mass into the resultant acceleration. Okay. Now, next we have Newton's third law of motion. That is the most common law you'll be hearing. Every action has an equal and opposite reaction. Okay. An action and reaction act on different bodies. So if this is the object and you're trying to push it with, let's say, this is a wall, okay? You're trying to push it with some 10 newtons of force. The wall will, so this is the action force that you're applying on the wall. And the wall will be exerting a reaction force on you, which is also of equal amount, okay? Now, next, normal contact force. Now, this contact force arises because there's an electromagnetic interaction between molecules of one surface with the another, like of this object and the surface. So because of that, because of those atoms or electrons, they collide with each other. Because of that, we have a contact force. Okay, it is always acts along the common normal of the two surfaces. So among these two surfaces, this contact force reacts perpendicular to the two surfaces. Okay, and it is always directed towards the system. Now, linear momentum, what would it be? It is a product of mass and velocity, right? And the rate of change of linear momentum is equals to force. Next, tension force. So, tension force, we normally see it come across this questions related to this in a pulley, right? So, in this pulley, we have two masses attached here, and one of the masses will be heavier. So, here as we can see, M1 is downward, M2 is upward. So, M1 must be greater than M2. Now, because of this mass being pulled downward, tension is acting on it. And the tension always acts in the upward direction. Okay. Tension in a massless string. And one more important thing, in a massless string, the tension will remain constant throughout the string. Okay. Now, so in an ideal pulley, when we talk about an ideal pulley, it is massless and frictionless. Okay. And an ideal string is inextensible and also massless. So there's no mass in this, and it cannot be extended. Okay. Now, analysis of transitional motion using NLM. So when we talk about any kind of motion, okay, so in that case, we have first analyze. So for example, even if we talk about this pulley of M1, okay, as we can see here. So on this pulley, we have, first we define the system, or what are the forces being acting on the system. And then that is the step on how to solve the tension or the gravity or the force or acceleration of the whole system. So for example, in your exam, you will be getting a pulley like this, and you will be asked to calculate the acceleration with which this mass M2 is going upward and M1 is coming downward. Okay. So how do you calculate? And you can be also asked to calculate the tension. So what is the process here? First, we define the system. We define all the environmental variables. Okay. Then we draw the free body diagram of each of the masses. So for example, here we have M1. Now M1 has upward tension T, a downward force, that is gravity pulling it downwards, right? M1G. And even after all these forces, this object is coming downwards with some acceleration A. So once we have drawn all this, we just equate all the forces. Okay. So M1A will be equal to see, since it is still coming downwards, so M1G must be greater than tension, that is pulling it upward, minus T. This is the first equation. Same kind of equation we will be getting for the second object. Let's say this is M2. So for M2 also there will be a downward force M2G, there will be an upward tension, and the object is still going upward, right? So the second direction of motion will be M2A T minus, right? First of all, T minus, because T is upward, and even after gravity, the object is still coming in upward direction with some acceleration A. So T minus M2G equals to M2A. Now we have two unknowns here, T and A. Using these two equations, can we solve the value for both? Right? So this is the whole process of calculating any kind of transitional motion. Okay. Now, next is transitional equilibrium. Now, throughout the system, we say that there is no net force. Net force throughout the system will be 0. Okay. Now, when we talk about any spring force, so the base formula or the only formula is the restoring force. So whenever the spring is pushed back, it tries to restore its initial state, and the formula for that is always Fs is equals to Kx. K is the spring constant and x is whatever amount of displacement you have done to the string. Okay, or spring, sorry. Now, when we talk about spring balance, the reading of a spring balance, it is Kx divided by G. So the spring balance is used to measure the weight of whatever different objects are there. Okay. Now, moving forward, variation of K with natural length. Now, at natural length, Kx is equals to constant. And as if we reduce the length, the value of K, if both ends of the spring are attached with the inertial mass, and then the sudden change in length of spring is not possible. Okay. Now, if magnitude of acceleration of each particle connected to a string is same, then net force acting on the string divided, then acceleration is equals to net force acting on the string by the total mass. Now, when we talk about pulleys or anything else, in that case, throughout the string, we ensure that we assume or ensure that the acceleration remains same. Okay. Now, moving forward, when we talk about a weighing machine, whatever reading that you will be seeing on the machine is what? Your reaction force divided by G. Okay. When object is put on a weighing machine, N is the normal force and N is the normal force between the objects and whatever the machine's reading. Now, next we have the pseudo force. Now, what is pseudo force? So, when we talk about frame of reference, we have two types of frames, inertial frames and non-inertial frames. Now, what are inertial and non-inertial frames? So, if the frame itself is moving or if the object in which you are itself is moving, then we consider it as a non-inertial frame. For example, if you are inside a car, okay, and the other person is standing on the street. So, if the person is standing on the street, for him, if there is no external force, this person is not going to move, right? But when you're sitting inside a car, even you are in rest, right? But the car is in motion. So, the car which is already, even if the person inside it is at rest, this frame itself is moving, right? So, whether the person chooses to move or not, or whether his state of rest remains same or not, does not depends upon the factor that whether there is force applied on the person. Okay. So, second law is not valid on a non-inertial frame. So, for example, if a frame itself is in motion, we apply a pseudo force to it. Now, for example, we have a lift. Now, this lift, normally a lift or any other object has a downward gravitational pull, right? Apart from that, if this lift is moving with some acceleration upward, let's say a pseudo force is applied in the opposite direction to it. This is the direction of pseudo force. That will be equal to the direction of motion. Pseudo force will also be equal to the acceleration part of the force will also be equal to A, and the mass will be M. Okay. So to balance and to make the non-inertial frame inertial, so that you can apply different laws of different Newton's law. Okay. Now, next we have the process to solve a pulley problem. Now, so to solve that, what are the assumptions or what is the process? So first of all, we take the acceleration of each block in some direction. Now, let's say for this pulley problem, this is a 3 kg block and this is a 4 kg block. But okay, and we are assuming for now that because of this 3 kg block, this will go down and this 4 kg block will start coming upward. Okay. Now, why we have 2t here and just t here? Because we have two strings here, right? These two strings is pulling it upward, so the resultant force here will be 2t upward. Okay. Now, we'll write we'll draw the FBD of each of these blocks one by one to calculate it. Okay. Let's see. So first, let's say we'll make the FBD. So this, for the first block, this will be what, 4 into g, and the upward force is 2t, and we have some acceleration that is going up as a2. Next, we'll draw the FBD of this one, that is again 3 kg. There will be a downward force of 3g, and there's upward tension T and some acceleration A1. Now, we'll balance all the forces. So, what does that mean? So, T minus 3g equals to what? Sorry. not t minus 3g. See, since there we have assumed that the acceleration already is downward, we'll write it as 3g minus t will be equals to 3a1. So that will be the force that will balance out this whole equation. Similarly, the another equation we'll be writing here. Since we are assuming that acceleration is going upward, so in that case, and if that is happening, that means that the tension here is stronger than the 4g force downward. So 2t minus 4g will be equal to 4a2. And using these two equations, you can solve the value for t and a. Okay. Now, if the acceleration comes negative, one important thing is there. If the acceleration comes positive, that means the direction that you assumed was correct. If the acceleration value comes negative, that means that the object was not going in downward direction. It was rather going. If let's say your a1 comes as minus 5, that means the object was not going downward. It was rather going upward. Okay. Now, moving on, next we have gravitation. Now, when we talk about gravitation, we have multiple things here. Okay, so let's start with what is the base formula for calculating gravitation, and then we'll move forward. So when we talk about gravitation, the first thing is the universal law of gravitation. So what does that mean? Every particle, whatever particle it is, it attracts each other, right? Some particles do not have enough mass or the strength to attract the other particles so that it can actually cause a response. But the larger the mass, it will be having the larger force of attraction. Now, so the formula for calculating the gravitational pull, F is equals to, one second, let me take a pen. Okay, it's not mentioned here, but this formula F is equals to G m1 or whatever is the other mass m2 upon the radius, the square. Okay, here this value of G is the gravitational constant. Okay, and if you know the dimension, if you remember we discussed dimensions, they can always easily ask what is the dimensional formula for this capital G. Okay, now, so gravitational force is always attractive in nature. It is a long range force. It can be experienced from a larger distance. And it is independent of medium. It does not depend on whether you are in water, air, in vacuum. Okay. Now, and one of the important thing is the gravitational force is one of the weakest fundamental force. Okay. This might be asked in your interviews most probably. But yeah, that is one thing that I would like to mention. Now, let's see. Then we have the value of G. What is G? G is the gravitational force or the pull we experience on Earth. Okay, that is equals to G capital M upon R. Right. Now, just G is the gravitational constant, M is the mass of Earth, and R is the radius. Okay, and the direction of this gravitational field is always negative. It is always towards the center. Okay. Next, we have the gravitational potential. Gravitational potential. What is the formula? G M upon R. That's it. That is the formula for gravitational potential. Okay, so that's about that. Then we have the variation of G with respect to height. So as we move at different heights or as we go deeper or away from the surface of Earth, the value of G changes. Okay, and for that also we have the formula here. So G at defined height, let's say when you're trying to go for a smaller distance, so that becomes 1 minus 2h upon R. H is the height and R is the distance. Okay. So as the height increases, the acceleration due to gravity, it starts decreasing. Okay, the force of gravitation will keep on decreasing with height. Now, as we go deeper on the surface of Earth, let's say you're trying to dig inside the surface of Earth. In that case, the gravitation as we go deep becomes G 1 minus the depth to which you are digging divided by R. Okay. Now, moving forward, we have satellites. And so what are satellites? Satellites are objects that are revolving around the surface, in the circular motion around Earth. Now these satellites can be, they can be of two types. First, we have natural satellites, that is the moon. Then we have our own man-made satellites or artificial satellites. These satellites are geostationary either. Now what does a geostationary satellite means? So these geostationary satellites, so they have this, the time period of their rotation around Earth is same as the revolution. The revolution time around Earth is 24 hours. So at each point of time, those satellites will be at the same place or pointing to the same particular object, same particular location. Now, next is the escape velocity. What is that? So escape velocity is the minimum amount of velocity required by any object or any, let's say, rocket, etc., to actually escape the surface of Earth, so that the gravitational pull is not enough to pull it back towards the ground. Okay, and that escape velocity is equals to 2 gm upon r. All right. So An object has to maintain that much velocity to actually escape the Earth's gravitational field. All right. Now, so when we talk about, this is what we talk about satellites. Okay. Next is the time period of the satellite. How much time will it take to complete one revolution? Okay, that is equals to 2 pi. It is not clearly mentioned here, but we can write it as 2 pi under root r square upon gm. Okay. Now, so then we discussed about geostationary satellites. Now, what are those? They are always pointed at the same place. So, for example, if this is Earth and the rotation speed of the Earth is 24 hours, right? It takes 24 hours for the Earth to complete one rotation. Now, these satellites, let's say, are pointed here and they cover one complete circle in 24 hours. So, at each point of time, they will be pointing at just one single location whether the Earth is rotating and whatever time, they'll be always pointing to some particular city, some particular place. Okay. Now, moving forward, we have the Kepler's law. So, we have for the first law of Kepler is planets revolve around the surface of Earth in elliptical orbit. Okay, that is the first law. Whatever planet is there, or even Earth or different planets, they always circle Earth in an elliptical orbit. What else is there? The center. This is the elliptical orbit. Sun is positioned as at one of the two foci of this orbit. Okay. So whenever we talk about ellipse, we have two foci, right? So sun is present either here or here. Okay. And lastly, the second law of Kepler is that, third law is that the distance covered by each of the planet, the area swept, let's say this is Earth, and it will travel from here to here, and this is where sun is. So I'll erase the other sun, the other foci. Okay. Now, the area that or the area covered by sun in, let's say, T1 time period, this area, and in the same amount of time it is traveling from here to here, let's say this is the same amount of time, T1. So the area covered will remain same in both the cases. Okay, this is the second law. That is, the line joining sun and the planet sweeps equal area in equal amount of time. Okay, and lastly we have the third law that says that the time period is proportional, the square of time period is proportional to the cube of distance or the orbital radius. Okay, that's about it. That's are the three Kepler's law. All right. Now, this covers most of whatever the given values are there. Check the value for what is, I'll just like you guys to check what is the value of G. Okay. Next, one of the important concept that also it should be covered is weightlessness. Now, when would an person and an object feel weightlessness? And there's no gravity. Now, that is not normally possible here, but you'll also feel weightlessness if the object is moving upward with gravity, with the force G. There we have a downward force G and downward acceleration G. And if your acceleration is equal to G, in that case, you will be experiencing weightlessness. Okay. So winding up the gravitational part, just ensure you remember the escape velocity formula, the formula for G, and the calculation of gravity at different heights, whether you're going above the surface of Earth or below the surface of Earth. Okay. Moving forward, next we have rotational motion. Now, when we talk about rotational motion, or any kind of motion, first of all. So, till now we have only discussed transitional motion when the object is moving in straight line, correct? Now, so when we talk about rotational motion or pure rotational motion, what happens is the object is rotating about some fixed axis, okay? And all the points on that object will perform circular motion. So, that is what a rotational motion is, okay? Now, in rotational motion, we have two very important theorems, parallel axis theorem and perpendicular axis theorem. So, but before we get started on that, first we'll discuss how Newton's law are applied to rotational motion. Now, when we talk about rotational motion, so in rotational motion, instead of having, in normal motion, we have your mass, we have velocity, we have distance, we have velocity, and we have acceleration. When we shift to rotational motion, the acceleration is taken as angular acceleration. Velocity is taken as omega or angular velocity. Speed or distance or displacement is taken as angular displacement denoted by theta. And the mass equivalent of object, when we talk about motion or rotational motion from normal motion, becomes inertia. So even if you don't understand the whole concept of inertia, of how it is going, moment of inertia, the mass equivalent in rotational motion is moment of inertia. That's about it. That is why we calculate moment of inertia across different angles, across different axes. Okay. Now let's see. So shifting to all the three equations of motions from straight normal equations to our angular momentum equation. So we'll get what? First equation of motion was S is equals to ut plus half at square. V is equals to u plus at. So we can also write it as omega final or final angular velocity is equals to initial angular velocity plus angular acceleration into t, right? Then we have S is equals to ut plus half at square, or displacement is equals to omega I into t plus 1 by 2 alpha t square. And lastly, v square equals u square plus 2as, that comes to omega final square is equals to omega initial square plus 2 alpha theta. That's about it, right? Now, moving on, we have radius of gyration. Radius of gyration is the ratio of moment of inertia with respect to mass of the object, okay? We denote it by k. So I becomes mk square and under root, right? So there is that. Now, next, first most important thing is parallel axis theorem. Now, what is parallel axis theorem? So whenever we have to calculate moment of inertia of across any axis, let's say if we have to calculate across axis A, okay? So in that case, the formula is moment of inertia. So we draw a parallel line, okay? If we have to calculate it across A, and this is the center of mass. Center of mass is the center point. Instead of taking the whole mass, if we consolidate it into one single point, that becomes your center of mass, okay? So the center, we draw a parallel line, parallel to AA, that is passing through center of mass, okay? So AA dash, parallel to AA dash, we have a line CC dash that passes through center of mass. Now, moment of inertia across AA dash will be moment of inertia across this one, CC dash, plus mass of this object plus distance between the two lines, a square. That is the parallel axis theorem. Now, so normally what happens is, you know the moment of inertia of a particular shape across its center of mass, okay? You know the moment of inertia of a disk across center of mass, you know moment of inertia of a cylinder across its center of mass, but you cannot know it across every random distance, right? So to calculate that, we use this formula. We take the moment of inertia across center of mass plus mass into distance square. That's about it, okay? Now, so for example, we have, let's say we have to calculate moment of inertia of this solid cylinder from this edge. So we know that moments of inertia of solid cylinder from center of mass is what? Mr square upon 4, right? Now, so what will be the moment of inertia across this edge? That will be then again mass, and we'll multiply the distance between these two lines, okay? And divided by, that's it. And that will give you your final answer, okay? The next important concept is perpendicular axis theorem, okay? Now, what is perpendicular axis theorem? So, any object will be having your three axes, x-axis, y-axis, and z-axis. So, we can use perpendicular, the perpendicular axis theorem says that the moment of inertia across if we have three perpendicular directions, so moment of inertia across z plane will be equal to moment of inertia across x plus moment of inertia across y, okay? That's about it. Now, for example, let's say if you have a disk here, okay? So, the moment of inertia along this line is mr square upon 4, and similar, so moment of inertia of a disk along its diameter is mr square upon 4. Now, if I want to calculate moment of inertia along this horizontal upward line, or the line coming outside towards the z-axis, so we'll just add these two moment of inertia, mr square plus by 4 plus mr square by 4, and this resultant mr square will be, and this resultant final answer will be mr square upon 2. That is the moment of inertia that is passing through the center of the disk coming outward, okay? So this is perpendicular axis theorem. Now, next important, so till now we discussed about mass analogous and velocity analogous. Now, when we talk about rotational motion, the force analogous of rotation in rotational motion is torque, okay? So what is torque? Torque is force applied at some angle or at some distance. So torque is equals to force R cross F. So where will you be seeing torque? Now see, you have seen a door, right? Door is fixed at one end. You apply some force at one end of the door. Okay. So in that case, the distance from the hinge of the door, let's say this side of the door is hinged. If you apply a force here, then you'll see the door gets closed very easily, right? Because it experiences a large amount of torque because the distance from here to here R becomes higher. Okay, so torque is a force analogous in rotational motion, and the formula for torque is R cross F. Okay, it is a vector quantity. Now moving forward, this topic we did not discuss in when talking about vectors. So next important thing is cross product. Okay, in vectors we also have cross products. Cross products has a magnitude as well as direction. Okay, you use these concepts to solve to take cross product of two vectors. And also you must be remembering we use the matrix method to solve for cross products, right? Now, when we talk about cross products, the I cross I always is 0. So similar crosses is always 0. Okay. But if we cross product I with j, you get k. So you can remember it like this: I, j, and k. If you go clockwise, I cross j will give you k, j cross k will give you I, and if you go anti-clockwise, I cross k will give you minus j. Okay, so that is the whole process. Okay, now moving forward, force couple. A pair of equal and opposite force is called a force couple, right? So if you are applying a force in this direction upward and this direction downward, this will there will be no net force there, but the torque will be present there. Okay, now next, angular momentum of next is the conservation of momentum concept. So now according to this, this is another example of conservation law where we say that the initial momentum and the final momentum is always the same, or the net change of momentum remains 0. Okay, next we have angular momentum of any particular particle, and the angular momentum of any particle is measured as r into linear momentum, or mvr. That is the angular momentum formula. Okay, we can also measure it as r into p. Okay, now moving forward, okay, then we have rolling motion. So now what does rolling motion means? Once we have a motion in which the transition, that is the forward motion, and the rotational motion both are happening together, that is called as the rolling motion. Okay, so we have pure transition where all the object is moving straight forward. Then we have pure rotation when the object is moving round and round around a fixed axis, and we have rolling motion where the object is performing translational motion also as well as rotating motion also. Okay, now moving forward, next we have circular motion. Okay, so when we talk about circular motion, the object rotates or performs a constant motion in circle with a fixed speed. Okay, and that is called as a uniform circular motion. Now what is angular velocity? See, when we talk about normal motion, we have velocity, that is change in displacement per unit time or change in distance per unit time. In angular motion, the value of theta changes. So the object, let's say it was from here, and this is the base point. Once it moves to here, it makes an angle theta. And next, so when we talk about theta, that is or angular displacement, that is change in the angle. Okay, so when we talk about angular velocity, that is the rate of change of this theta with respect to time. Right? Now moving forward, next we have angular acceleration. So the rate of change of this angular velocity is known as angular acceleration, or also known as alpha. All right, in the same case we have instantaneous angular acceleration and instantaneous angular velocity, just like we discussed before, at that particular moment, and averages throughout the motion. Right? Now next we have a non-uniform circular motion. What does that mean? In uniform motion, the acceleration is constant, the velocity is constant, but when the acceleration changes with respect to time, that forms us as a non-uniform circular motion. Okay, next we have curvilinear motion, a motion in which we have velocity and theta. The motion isn't happening at a particular angle. Okay, now moving forward, radius of curvature, that is this angle, or the radius at which when we talk about any curvilinear motion, a motion like this, the angle or the radius at this, let's say if you draw a circle here, This is the radius of curvature, okay? And this is the center of curvature, this point, okay? Now, so moving forward, and we can also write one very important thing when we talk about angular and normal motion is we can always write horizontal acceleration, horizontal velocity v is equals to omega r, okay? Angular velocity into r, all right? Now, moving forward, we have dynamics of a circular motion. The same formulas or the same resultant will be there. The total force will be constant throughout the motion. Ma will be, we can also write it as force, when we talk about circular motion. So in that case, we can always write A is equals to mv square upon r. Now this mv square upon r, or whatever is, or m omega square upon r, this is your centripetal force. So for any kind of circular motion to happen, if the object is moving in circular motion, this is the horizontal velocity v, and there is a force that is pulling the motion towards the center, so that the object keeps on because of this v, the object keeps on rotating, but the central force that is pulling it towards the center, this is the centripetal force, okay? Now this centripetal force is not exactly, we cannot say that this is a particular type of force. This centripetal force can be a gravitational force if there is the moon that is rotating around earth in circular motion, okay? In that case, this centripetal force is your gravitational pull. When we talk about electrostatics, and because of that there is the motion, that also, if it is moving in circular motion, that will also be a centripetal force. So whatever force is trying to pull the object towards the center is the centripetal force, all right? Next, centrifugal force. Now, what is centrifugal force? Centrifugal force is the reaction force. Now, for example, when we were discussing that, okay, this is a wall and a person is trying to push the wall responds back. Similarly, the reaction force to the centripetal force is centrifugal force, so that the object does not collide in towards the center. So the centrifugal force is just the reaction force to the centripetal force, and the centrifugal force is always equal to centripetal force, okay? And that is mv square on r. That's about it. Now, next, moving forward, we have fluids. Now, when we talk about fluids in general, it is compressible, it composes your gases and liquids. But for our calculation, for our purposes, we talk about ideal fluids. Now, ideal fluids are incompressible in nature, okay? So, when we talk about fluids, we have pressure, we have, so as we go down in a liquid, the pressure increases, right? And the pressure or the force that is, it's taken as rho GH, okay? That is the pressure as we go down inside a fluid. Now, one of the very important concepts of in fluid is buoyant force. So whenever you submerge an object in a fluid or in any other liquid substance, what happens is we experience an upward force. Apart from gravity, that this is the object that is being submerged here, this will be experiencing a downward force because of gravity, but an upward force is also experienced by the object, and that upward force is equal to the amount of liquid that is displaced by this solid object, okay? So the buoyant force will be equal to rho into g into h. Now rho is the density of the liquid, okay, that is replaced, and into area that is replaced by that object, okay? This is the buoyant force. Now, what is Archimedes' principle? Archimedes' principle states that if the buoyant force or the amount of a fluid replaced, or the weight of the fluid that is replaced, that is rho into the volume of the solid surface into g. That is the buoyant force, right? Rho of the liquid and volume of the solid. So that multiplied by gravity is the weight of fluid displaced, right? If that fluid displaced, that buoyant force is greater than the gravitational force, then the object will float, right? Because gravitational force is pulling it downward, the buoyant force is pushing it upward. If the buoyant force is greater, the object will float. If the buoyant force is equal, it will be fully submerged, and if the buoyant force is less, the object will sink. So these are the three conditions, and this is the Archimedes principle. Now, when we talk about ideal fluid, it is incompressible and non-viscous in nature, all right? Now, and the volume, one more thing is volume that passes through any, let's say we are passing the liquid through a pipe or any other structure. The volume that is flowing through it per unit time is always constant, okay? Now, moving forward, we have Bernoulli's principle. Now, Bernoulli's principle is applied for dynamic fluid when the fluid is in flowing nature, okay? And that says that pressure plus rho GH plus half rho V square, rho is the density, is always constant, okay? And based on this, we use it whenever we have, so even if let's say the velocity is 0 or the fluid is at rest, this part will become 0 and P plus rho GH is always remains constant, right? Next, we have equation of continuity, that is whatever volume, let's say you have a fixed volume of container size, right? Fixed size of container. So whatever volume is coming out, AV1, the same amount of volume will be leaving the fluid, okay? So if V1 is the velocity with which the water is coming in and A1 is the area, the amount of the speed with which the water will be leaving, let's say that is V2. And if the outer area is small, the velocity with which the water will be leaving will be higher, okay? Now, next, ideal fluid cannot sustain shear strain. What is shear strain? The strain, so when you have a solid object like this, okay? And if you apply a force in tangential direction. So ideal fluid cannot sustain shear strain, okay? Now, and also as we discussed, as you go down, let's say this is a water container and the external air pressure is P naught. As you keep going down, let's say at this point H, what will be the pressure here? That will be P naught plus the rho is the density of the fluid, H is the height that you have gone down into G. That is the variation of pressure as we go down, okay? Next, we have Pascal's law. What does that say? Whenever there is an external pressure that is given at any part of the fluid, it is transmitted throughout the liquid, undiminished, okay? Next, we have a U-shaped tube. Now, this is used in a lot of your devices. For example, you have that lift that carries on heavy car washes are used, okay, for that. So, if you apply some pressure here and if you apply some force here, the same amount of force will be the same, that pressure will be distributed here, and the same amount of force will or the same amount of pressure will be exerted in the other side of the fluid, okay? And on this concept, those devices work. So let's say if you're applying some force F1 here, so F1 and that is moving some area A1 will be equal to whatever external force that will go out, F2, and area, this area of this cross section A2, okay? Now, next is a barometer. And so what is a barometer? It is a device that is used to calculate pressure, okay, throughout whatever object. It is used to calculate the volume of the object. I mean the pressure of the external environment. Next, we have the Stokes law. Now, Stokes law is about drag force, or the force that is experienced by let's say a spherical object is there and it is put inside a fluid. So it will be moving with some velocity v. So now this force that is being experienced by it, that will be equal to 6 pi nu r into v. V is the velocity of the object and nu is the viscosity of this liquid, okay? Now, moving forward, mechanical properties of fluids are there, but that's about it, okay? Now, next is surface tension. So whenever we have a surface or any object, okay, so there is a horizontal, or along the surface we have a horizontal tension on the surface that is maintained, and that surface tension you might have also seen it when you have a glass of water and you add one extra drop. Even if the glass is full, the drop does not fall down because that is stretched throughout the surface, okay? And the surface tension on the surface is always greater than the tension inside the surface. And we calculate surface tension as force per unit length across the surface. So example, if this is the surface of water, and for this length, if you are calculating, the surface tension will be force per unit this length, okay? Now, surface energy is equal to surface tension into whatever surface area is there. All right. Next, we have the contact angle. So whenever we have a liquid, or it can be water, it can be mercury. So whatever angle that makes with the vessel, that is called as the contact angle, okay? So for glass vessel and water, the contact angle is less than 90 degree. For silver vessel and water, the contact angle is exactly 90 degree. And when we talk about mercury and glass vessel, you'll see there is a curve upward, right? That because the contact angle is greater than 90 degree, okay? One another important thing is the force between two different types of molecule is called adhesive force. This is the force that acts between your paper and glue when you attach, okay? And the force between the same type of object is called cohesive force. Same objects, same molecules will be attached towards each other because of cohesive force, okay? Now, a capillary tube is a very thin tube, okay? a very thin tube, when you submerge it in water, because of this cohesive force, let's say water molecule, it will try to rise, okay, because the attraction force is there, okay. And that here, if it is rising up, the attraction force between the glass and the water is higher, or the adhesive force is higher. And the height of this capillary tube is 2s upon rho gh. S is the surface tension, rho is the density, g and r, okay. Now, excess pressure inside a drop of air. See, if any drop is maintaining a circular shape, it is because there is an extra pressure inside it, right? And it is maintaining a circular shape to maintain the lowest possible surface area, okay. Now, excess pressure inside a drop of air is 2s upon r. Inside a soap bubble, since there is two surfaces, there is a bubble and inside it there is another layer, and then it is hollow. So for that case, it is 4s upon r. And when we talk about an air bubble in water, it is just a single surface, so it is 2s upon r again. All right. Next are one of the most important chapters, thermodynamics. Yeah, the similar concepts of this in your chemistry as well. The only difference is in work done. Okay. Now, when we talk about thermodynamical process, we have different types of process. Isochoric process. In isochoric process, the volume remains constant. So the volume is constant, and we have three units when we talk about thermodynamics. We have heat energy, the internal energy, and work done. So one of the base formula of thermodynamics, or the first law of thermodynamics, is whatever the heat you are supplying to an object, it gets converted into the internal energy of the object, or it is reverted as the work done. Okay. So now if heat is applied, we write it as positive heat, or if heat is lost, it will be applied as negative heat. If the internal energy increases, we write it as positive U. If it decreases, we write it as negative U. If the gas is doing some work, if the work is done by the object, in that case, it is taken as positive. If it is work done by the gas, it is taken as negative. Okay. Now, let's go back to this processes. So if the volume remains constant, okay, if the volume remains constant, the work done is zero in that process. In that case, so whatever energy or whatever heat you will supply to the object or to the process, to the system, gets converted. All of the heat is changed to internal energy. Okay, and the formula to calculate it is NCV delta T. Okay. Now, next is isobaric process. In isobaric process, the pressure remains constant. Okay. So whatever the formula for heat remains same, delta Q remains same, that is NCP delta T, and the work done is NR. R is the gas constant into delta T, or whatever the change in temperature is there. Moving forward, isothermal process. Now in isothermal process, the temperature is kept constant. So if the temperature is not changing, internal energy cannot change. So delta U in this case is equal to 0. Work done is nRT ln change in volume. Okay. Now, moving forward, Cp minus Cv is equals to R is the Mayer's equation, and R is the gas constant. Cp is at constant pressure and Cv is at constant volume. And the ratio of these two is denoted by gamma, is known as the adiabatic constant. Now, for different types of gases, it is monatomic, diatomic, or polyatomic gases. The value of Cp and Cv are related like this. F is the degree of freedom here, and the ratio of it is denoted by gamma. This you should be knowing for solving a lot of equations, right? Now, work done by the gas. So whenever there is a gas that that gas is increasing some pressure and doing some work, that work done is equals to whatever the pressure was inside the gas and the change in volume. So work done is equals to P delta V. And internal energy, the formula for internal energy is F upon 2 nRT. Internal energy is the energy of the molecules. Because of the motion of these electrons, atoms, molecules, that is known as the internal energy. Next, we have the adiabatic process. Now, in adiabatic process, there is no external heat supplied. So, delta Q is equals to 0. Whatever work is done or whatever change in the energies is there, is if work gets converted to internal energy, or internal energy is converted to work done. Okay. So, delta Q is 0. So, W is equals to minus delta U. Next, we have polytropic process, in which PV to the power x is constant. In that case, this is the formula for work done, nR delta T into 1 minus x. Okay. Now, moving forward, next we have ray optics. So, in ray optics, let's start from one by one. First of all, let's say we have two mirrors that are placed at an angle theta. Okay. So, how many reflections will be formed because of this theta? So, number of reflections so you divide 360 divided by whatever value of theta you are getting. and that will give you the value of n. If the n is an even number, number of images formed will be n minus 1. If n is an odd number, number of images formed will be n. And if n is not an integer, you have to count. Okay. Now, next is a focal length. So for focal length, we talk about mirrors. Okay. So you have a curve mirror. So what is a curve mirror? We have concave mirror and convex mirror. So these mirrors are cut out from a circular mirror. Okay. So now if you're cutting it out from a circular mirror, this circle will have some radius, right? That is the radius of curvature. And radius of curvature by 2 is your focal length. Now, magnification, if you have a curve mirror, what will happen is, if you have a concave or convex mirror, whatever it is. So, let's say this is your object and this is where you have placed your object. This is your mirror and the image is found somewhere here. So, how large or how small will that image be? Or will it be larger than the object or smaller than the object? So, that is the magnification. And magnification is the ratio of the position of image divided by position of object. Okay. Now, next we have linear magnification. That is height of image by height of object. If it is greater than 1, then the image will be enlarged. If it is less than 1, the image will be diminished. Okay. Then we have net magnification. Height of image minus final minus height of object. Okay. And if you have multiple mirrors or multiple lenses you are using, then we just multiply the magnification. Okay. Next is the mirror equation. That is 1 by v, where v is the position of object. U is the position of object. Sorry. Plus 1 by v, that is the position of image, is equals to focus. Okay. Now, next we have the tracing diagram. So, instead of going into all of the whole scenarios, one of the base concepts that you can understand about ray optics is that, let's say if you have a mirror, okay, this is your focal length and this is your radius of curvature. If an object, if a ray starts parallel, it always passes through focus. If a ray passes from radius of if a ray passes from radius of curvature initially, it will return back through the same line. All right, and if it passes from focus, it will return parallel. Now, with these three concepts, you can draw image of any kind of image. Okay, whatever is the position of object, you only need the rays to coincide once. Okay, so you can use any of the three concepts to deduce your outcome. Now, moving back to where we were. So, if a ray is parallel to principal axis after reflection, it will pass through focus. If a ray is parallel to principal axis after reflection, in case of a convex mirror, it will seem like it is passing through focus. In a convex mirror, the focus is behind the mirror, right? Now, next we have properties of image formed by a plane mirror. So, if you're talking about a plane mirror, the image is always virtual. It is of the same size as of the object. And what else? The height of image is always same. And it is formed at the same distance from where you're standing. One more thing, to actually see one's whole self in a mirror, the height of the mirror should be greater than half of the person's height. Okay. Now, next is laws of reflection. What are the laws of reflection? Angle of incidence is equals to angle of reflection, and incident ray, reflected ray, and the normal to the mirror all lies in the same plane. And velocity of object and velocity of image is equal in case of a plane mirror, right? Next, if the rays actually meet in the real side, for example, if I'm saying if this is a mirror and this is the object, if you pass it, if it is going parallel, it will seem like it is passing through focus. If this is the focus, okay, and if it is going through the focus, let's say if it is going through the focus, something like that, it will pass parallel. Now, if these two rays are actually meeting, not behind the mirror, if it is meeting here somewhere in the left side of the mirror, then we form a real image. Now, for example, you can see a real image in case of this. Okay, so let's say this is your focus and this is radius of curvature. So if it is passing parallel, it will pass through focus. If it is passing through focus, it will pass parallel, and these two rays are meeting here. They are actually meeting. So this will form a real image. But in this case, I'll just redraw this once for you. So let's take a convex mirror. Okay, this is a convex mirror. So now if this is the object and you pass a parallel ray, it will seem like it is coming out from the focus, right? And if you pass a ray that will seem like it is passing through the focus, it will pass this is, let's say, this is passing through the focus, it will go out parallel. If you draw these two rays back, they are meeting somewhere here. They are not actually meeting, they seem like they are meeting. So this kind of image will be a virtual image. Okay. Now, moving forward, we have the sign convection. The sign convection of a mirror is mostly similar to whatever the sign convention we have of a normal Cartesian plane. So let's take this as the point of the pole. If this is your mirror, this is the pole. Okay, so whatever stands on the left side is taken as negative, whatever stands on the right is taken as positive, whatever comes upward is taken as positive, whatever comes downward is taken as negative. That's about it. Okay, now moving forward, we have refraction. Now what is refraction? So see, so when the light waves travels from one medium to another medium, it bends, okay? And that bending of light is known as refraction. So for example, if you have if this is two mediums, the separation, this is water, this is air, and a light enters here, okay? One second. Water is denser than air, right? So the light ray always bends towards the normal of the denser medium. It will bend like this, okay? This is the process of refraction. Now, refractive index of any medium is speed of light in vacuum divided by speed of light in that medium. And laws of refraction states that incident ray, reflected ray, and the normal to the surface always lies in the same plane. Okay. And then we have the Snell's law, that is mu1 sin I is equals to mu2 sin R, where mu1 is the refractive index of incident ray and mu2 is the refractive index of reflected ray. Okay. Then, where can we see these refractions in our day-to-day life? Early sunrise, you know, you can see that the atmosphere seems like oranges, right? Then we have apparent flattening of suns at the sunset, twinkling of stars. These are all examples of reflection. Now, next we have, when we talk about a glass slab, light enters through the slab and the slab is thicker and it exits through another line. They are not of the same, they are not in the same plane, okay? So, they are not, I'll show you through a diagram here. So let's say this is a glass slab, okay? If the light is entering here, it bends. This is a normal. It bends a little here and it moves forward like this. Then again, it is exiting from a denser medium to a rarer medium. It will bend away from the normal. So this was where the light was supposed to go. And this is where it went. So this shift happens in the case of a glass slab. Similarly, you'll also see that, you know, if you have very clean water let's say in a lake, you will see that you'll feel like the water is actually does not seem deep enough, but that is the apparent depth. You're not able to exactly see what is the actual depth of the water. So apparent depth is equals to HI, that is the depth that you are able to see, that is equals to HO, that is the actual depth, divided by mu I upon R, okay? And the shift is equals to height of object divided by 1 minus mu I upon R. Moving forward, we have Lensmaker's formula. That says that is 1 by f is equals to mu2 minus v1, that is the ratio of refractive index of the two objects, minus 1 divided by 1 by r1 plus 1 by r2. r1 and r2 are the radius of curvature of the two sides of the lenses. Now, again we have the lens formula, 1 by v minus 1 by u is equals to 1 by f. Remember this negative sign here, subtraction. In the mirror formula, it was 1 by v plus 1 by, okay? Now, the same scenario happens here also. We have the ratio magnification, that is the ratio of object height, image height by the ratio of object height, okay? Moving forward. Next we have a prism. Now in case of prism also, you will get the refraction. So light enters here, it gets refracted, then again it leaves to the other surface and it again gets refracted. So this is the incident ray and this is the emergent ray, okay? So if you talk about a prism, that is like this. Light ray was supposed to enter here, that is the incident ray. It bends because it goes into a denser medium, and again as it leaves the prism, it again bends. And this is the emergent ray. So the light that was supposed to go like this went out like this. So there is an angle of deviation. Okay, this angle of deviation delta is equals to I plus E minus A. A is the angle of the prism. Okay, and this is the graph of deviation. Now, next we have silvering of a mirror. So to ensure that the mirror is able to reflect, behind the mirror we put a silver layer of it. Okay, or a reflecting layer. Now, when we keep lenses close to each other, in that case, the focal length or the equivalent focal length of the multiple lenses or multiple mirrors is 1 by f1 plus 1 by f2 plus 1 by f3 can be added. Power is whatever is the gain or increase in the focal length, increase in the image size. Okay, and the power of multiple lenses is added together. The power is the SI unit of power is diopter. Okay. Now, next is dispersion. So whenever a white light enters a prism, what happens is white light is made up of different colors: violet, indigo, green, yellow, orange, red. Okay, different colors of the lights, they deviate at a different angle. Okay, and that is why when the light exits the prism, different colors deviates lesser, lesser, or lesser. So violet deviates the most. So you can see it as it goes down, and the red deviates the least. Okay, moving forward, we'll talk about optical instruments and defects of eyes. So see, when we talk about eyes, we have this whole structure given here. So if we just zoom in a little, this is your eye. This is the vitreous gel. Okay, and inside the eye we have a small opening here, and we have a lens here. Now this small opening is called the pupil, and the muscles that hold those eyes lenses together is called iris. Okay, and then we have the lens here inside the eyes, and we have the rectum muscles that keeps the eyes intact and in place. Then we have the vitreous gel that is filled inside the eye, and we have this is the retina where the image is being formed, and the whatever image is being formed, that image is transported to brain using these optic nerves. Now, what happens when you are constantly fixed to your screen or constantly seeing at a smaller distance? You get nearsightedness and farsightedness. Now, what does that sightedness? What happens is, since you are looking at a closer screen for such long amount of time, your eye muscles get fixed on it. So you are only able to see nearby objects. The far away objects are blurry in nature. Okay, this can be fixed using a concave lens. Okay, the far away objects or the images coming from far, they are formed before this retina. Okay. Next, we have farsightedness. That farsightedness mostly comes from age. Okay, people as they grow old, they have this farsightedness. What happens is you're able to see distant images clearly, but the nearby objects. For that, your eyes are so used to viewing the far object that the image formed is behind the retina. Okay, to fix that, we use a concave lens. Then we have astigmatism. In this, what happens? You're not able to see crisscross or objects clearly on the surface. Okay, so to fix that, we use a cylindrical lens. Next, we have presbyopia. In old age, near point is increased as much as we grow older, the near point or the ability of us to see the nearest possible object, it increases to 2 centimeters. Next, we have optical instruments like a simple microscope. Now, in a simple microscope, the angular magnification is D upon F. Okay, where D is the distance at which the object is seen and F is the focal length. Okay, and the image of the least vision of the distant vision, or how distinctly you will be able to differentiate between these two placed objects, that will be DF plus 1. Next, we have a compound microscope. In a compound microscope, we have an objective, that is objective lens, that is kept near to the object, and an eyepiece that is closer to the eye. In that case, the total magnification becomes, we multiply those two. Okay, and that is 1 by FO, L by FO into DE by FE. Okay, and the total magnification is calculated using this formula. Okay, next we have a telescope. In the telescope also we have 2 magnifying lenses, and the magnifying power becomes beta upon alpha. Okay, or FO upon UE or FO upon FE. Moving forward, next we'll start with electrostatics. Now, electrostatics talk about charges which are at rest. Okay, so we have 2 types of charges, positive charge and negative charge. So similar type of charges, they repel each other, whereas opposite charges, they attract each other. And charges, you can they are quantized in nature. So you can only the smallest amount of charge you can move is 1 coulomb of charge. You cannot move 1.5 coulomb. You cannot get 2.6 coulomb. The only thing you can get is 1, 2, 3. Okay, they are quantized in nature, and you can add them like real numbers. Okay. Now, charge of isolated system remains conserved. So you cannot inside a particular system, the charge will remain always constant. It can switch between one object to other object, but it always remains constant. Charge is invariant from the frame of reference. Now, when the two charges are placed, they either attract or repel each other with some force. Now, that force is equals to 1 by 4 pi epsilon naught q1 q2 upon r square. This is the force, where q1 q2 is the charge of the two objects and r is the distance between them. The value of epsilon naught is 8.85 10 to the power minus 12. Okay. Now, in vector form, we write it like this. Next, we have the electric field due to point charges. Now, let's say we have a point charge with the charge capacity Q. Because of that, around it, you will be feeling a field. Okay, there will be a field around which an external charge will experience some force, and that electric field is kq upon r square. Okay. Now, if we have a system of charge, so because of that, the electric field we get just added on E1 plus E2 plus E3 and as on. Now, if we have a perpendicular bisector of line joining two charges here, so we have one charge here and one charge here, both are of same type. In that case, the net charge is calculated like this. Okay. Now, moving forward. Now, if we have a uniformly charged ring, you have a ring. Okay. On the axis of this, on this line, the electric field is calculated like this. Okay. This is the formula. KQ, X is the distance where you are placing the charge or placing the object, or the distance where you will be experiencing this electric charge. Okay. Electric field intensity due to uniformly charged thin straight wire. Now, if you have a thin straight wire and let's say at some distance here, B, what will be the electric field at this distance? That is K lambda. Lambda is the charge per unit length. Okay. Divided by R or D, that is the distance, plus sine theta. Theta is the angle here, theta 1 and theta 2. Okay. And if you have an extremely long parallel wire, that is K lambda R upon cos theta 1 minus cos theta. Next. If you have an infinitely long wire, in that case, the electric field is perpendicular at a perpendicular distance is K lambda sine theta 1 and sine theta 2. And if it is infinitely long, this theta 1 and theta 2 will become C. If this is an infinitely long wire, this theta 1 and theta 2 becomes 1, right? Because this angle is very large, or this is almost equal to 90 degrees. So you get 2K lambda upon R. Alright. Now, electric field due to uniformly charged semi-infinite long wire. So one side is stretching constantly. The same concept is there also. Now, electric field due to uniformly charged arc at the center of curvature. If this is an arc and you have to calculate electric field here. So the formula 2K lambda upon R minus sine alpha by 2. Alpha is the angle obtained by this arc. Okay. Electric field intensity on axis of a uniformly charged disk. If you have a disk will have some charge per unit area. And at some axis point here, if you have to calculate the charge, this is the formula 1 by 2 epsilon naught 1 minus 2 cos theta. Okay. Electric field due to one positive and negative charge. This is how the electric field will look like. From all the positive charges, the field lines start and they all conclude at the negative charge. Okay. Electric field lines due to two positively, this is not correct. Due to two positively charged objects, the field lines will look like this. All going out, but there will be no point where it gets submerged. Okay. Now, moving forward. Motion of charged particles in an electric field. So if a charged particle is moving in an electric field, the force that is experienced is Q into E. E is the electric field and Q is the charge of the particles. Okay. Next is electric flux. Electric flux is E dot A. Electric field. So what electric flux is amount of charge of electric field that is passing through a defined unit of area. That is electric flux. That is E dot A. Okay. Then net flux linked to a closed. If we have a closed surface, okay, in that case also the net flux, that is E into whatever area is there. This is called the net flux around a closed surface. So for example, if this is a cuboid and inside this we have a charge, let's say Q. So whatever amount of electric field is getting out of these 6 surfaces is the flux linked inside a closed surface. Now, then we have Gauss law. This is one of the most important laws in this chapter. So what Gauss law states is the amount of electric flux inside a closed surface is equal to E dot dA that is equal to whatever charge is inside the surface. Let's say we have charge Q divided by epsilon naught. So out of 6 surfaces, we have Q upon epsilon naught charge that is being passed out. Epsilon naught flux that is being radiated. Electric field due to a thin spherical shell. Now, if you have a thin spherical shell that is charged in nature, electric field is kq upon r square. Okay. Now, and if you are inside the shell, there will be no electric field inside it. Okay. Now, if you have again a solid sphere, in that case also, if you go outside the radius, I mean this is the radius of the sphere. If you point at object outside it, it is kq upon r square. If you go inside it, the formula is rho r upon 3 epsilon naught. Okay. Why rho r? So see, if you calculate it here, the intensity will be covering from only just this range. Okay, just because of that. Electric field intensity due to long uniformly charged solid cylinder. This is the formula, rho re upon re epsilon naught. If we are talking about the cylinder, if you're calculating it somewhere inside the cylinder, if you're calculating somewhere outside, it is rho re, rho r square upon 2 epsilon naught into r. Okay. Now, electric field due to a long uniformly charged cylinder shell. The same concept. See, you have to know some basics of it, of the electric field intensity. For example, the solid sphere you should be knowing. Then the circle, the disc. That's about it. Not a lot of it. And the infinitely charged wire, normal wire. All these might be asked very frequently in an exam. Electric field intensity due to a infinitely long charged wire. This we already covered. Electric field due to infinitely long sheet. If you have a sheet that is charged, sigma will be the charge per unit area and electric field is sigma upon 2 epsilon. Okay. Next, potential energy of system of two charges. If you have a charge, two charges placed here, what will be the potential energy? That is k q1 q2 upon r. Okay. Now, work done by electrostatic force. If you're trying to bring a charge inside an electric field in a given particular range, so how much work will be required to be done to bring the charge externally inside this electric field? That work done is equals to k q1 q2 upon r, whatever was the initial position, minus k q1 q2 upon r, that is the final position. Okay. Next, work energy theorem holds true here also. Kinetic energy initially and kinetic whatever work is done will be equal to change in the kinetic energy. Okay. Next, we have the electrical potential. So the change in electric potential for bringing a charge from one place to another, or delta V, is equals to E dot dr, or whatever distance you're trying to bring inside it. Okay. Interactional potential energy and self potential energy. Now, a self potential energy is whatever potential energy of the object is there because of itself. Okay. And when an external charge is brought inside the same range, because of that, whatever potential it is gaining, that is the interactional potential energy. Okay. Next, electric potential due to a these are the just formulas. Uniformly charged spherical shell, solid sphere. Okay. Now, equipotential surface. So those surfaces where the potential, and even if you try to move an object from one place to another, there is no change in potential, are known as equipotential surface. Electric field is perpendicular to equipotential surface. So let's say if this is a charged wire, so at a fixed length, this point, this point, this point, this will be equipotential. There is no change in potential energy. Okay. So an electric field is always acting parallel to the equipotential surface. Perpendicular. Okay. Net work done when you try to move some charge on an equipotential surface is always zero. Next, we have a dipole. Now, what is a dipole? We have two equal and opposite charges separated by some distance. That is called a dipole. Dipole moment is charge into distance between the two charges. Okay. Now, if we have a dipole, and from that dipole, if you have to calculate at some general point, the electric field is Kp upon r cube under root 3 cos square theta plus 1. Theta is the angle here. Okay. Next, electric potential at a generic point. So if you have some random point, this is the formula for it. Torque, again, the torque because of electric field. So if we have, let's say, this is your charge. Okay. This is your dipole. So the positive charge will experience an upward force, the negative charge will experience a downward force. And because of that, there is a torque present there, right? And what is the formula for torque here? P cross E. P is the dipole moment and E is the electric field. Next, electrical potential energy of an electric dipole. Now, what is the potential energy of the dipole that is normally existing? So, in stable situation, the dipole, this is the electric field and this is the dipole. They are parallel to each other. So, the potential energy is minus PE. Now, if you try to move it at some particular angle, it becomes PE cos theta. Okay, that is the potential energy. Now, induced charge in case of a concentric sphere. So if there is a concentric sphere inside it, if you are trying to induce some charge, it is Q enclosed by epsilon naught, like we discussed in Gauss law. Now, electric potential due to a spherical conductor. Now, if you have a spherical conductor, the same formulas that we discussed previously. Okay. Next, we have a Faraday's cage. In case, what does the Faraday's cage do? In case if we have a shell, okay, that is charged. Inside the shell, there will be no electromagnetic field line. That is a Faraday's cage. Okay. Next, conductor with cavity. Inside this hollow space, electric field intensity inside the cavity will be 0. There is no induced charge on the surface of the cavity. Okay, and the potential inside the cavity is same as the potential of the conductor. Moving forward, if we have a parallel conducting plate, these are the two parallel conducting plates. On the surface of plates, equal and opposite charge appear. Okay, Q1 and Q2. And on the outermost plate, the charge is Q1 upon 2, because on the both sides, the charges will be split. All right. Next, we have electrostatics pressure. P is equals to sigma square upon 2 epsilon naught. Okay. And whenever there is an electric field, the energy density is 1 by 2 epsilon naught E square. Okay. And E square is the electric field intensity here. Next, effect of medium on the net electrostatic force. And there is two objects, and if we place it in, normally we consider epsilon naught in case of vacuum. But if we place it in some particular medium, we have to take epsilon naught of that particular value of E of that particular medium. That is called medium of permittivity. Okay. Now, moving on. Next, we have the capacitor. So, when we talk about capacitor, what is a capacitor? So, it is just two parallel plates that are having charge. Okay. So, that are equal and oppositely charged. If this side is positively charged, having 5 coulombs, this side will be negatively charged, having 5 coulombs. Okay. So, the capacity of whatever capacitor it is depends upon the shape and size of the plate, the distance between the plate, and whatever medium is there between these two plates. The capacitors are two conducting objects in which there is a medium and insulating medium between them. Okay. Now, for a parallel plate capacitor, the value of C is A epsilon naught upon D. Okay. For a spherical capacitor, the capacitance is 4 pi epsilon naught AB into B minus A, where B and A is the radius of the two shells. Then we have cylindrical capacitor. The capacitance is 2 pi epsilon naught L. L is the length of the cylinder. Ln B by A. Normally, you will be seeing only parallel plate capacitors. Okay. Next. Moving forward, we have this. So, before we cover this part, we'll just check once about current. Okay. So, here we have current electricity. Now, when we talk about electrostatics, that means charges are at rest. When the charges are in motion, we see current. So, flow of charge per unit time is known as current. Okay. In current electricity, we have two Kirchhoff's law, KVL and KCL. What does KCL say? That current law says that at any junction, the amount of incoming current and the amount of outgoing current is always equal. So, current entering is equals to current leaving. Next, KVL states that the algebraic sum of the change in potential around a closed circle or closed loop is always equal to 0. Okay. Now, node analysis. So, potential in a circuit at a junction. So, to calculate whatever is the potential at some point, or to calculate a flow of current, we use this KVL and KCL and apply at the junction. Now, we have parallel combination. So, next we have resistors. Now, what are resistors? Resistors are devices which offer hindrance in the flow of current. Okay. So, resistors can be kept in series as well as in parallel. So, if they are in series, the resistance is just added upon I1 plus I2 plus I3 and so on. If they are placed in parallel, we use R1 by R1 plus 1 by R2 and so on. Okay. Now, then we have batteries. Now, batteries, they have voltage and actual supply. Okay. So, if the battery is saying it is of 5 volts, so that means it is able to supply. Does that mean that it is able to supply 5 volts? No, actually what happens is some part of this voltage is also consumed by the internal resistor of the battery. Okay. So, when we actually have batteries in series combination, we add that internal resistance of the battery also in the circuit's resistance. Okay. In series combination of the battery, we just normally add the voltage of E1, E2, E3 and so on. In parallel combination, what we do, we take the ratio E1 by R1 plus E2 by R2 and we go on. Okay. Now, How much power is delivered through a device? So the calculation of power is done by V into I. V is the voltage and I is the current that is flowing through it. Okay. Now, maximum power transmission theorem, what does it say? The power consumed by a load resistor will be maximum where its value is equal to the internal resistance of the battery. Okay. Next is current density, amount of current flowing through a cross-sectional area, that is denoted by J, that is I upon A. Okay. Now, how much is the power consumed by a resistor? Just now we saw VI. We can also write it as I square I or V square R, whatever is the value given to you. Next, steady current I is same throughout all cross sections of current, that is given about when talk about current. Next, we have drift velocity. Now, what is drift velocity? So, the average time between two collisions that happens when the flow of current is happening, that is known as the drift velocity. Tau is known as the drift velocity. Drift velocity is the speed at which the current is flowing. Okay. Next, we have Ohm's law. So, what does Ohm's law states? V is equals to I. That is Ohm's law. R is the resistance. Now, so as you increase current, as you increase voltage, the flow of current increases. So Ohm's law states that voltage is proportional to current, and to remove this proportionality constant, we have the value R. Okay. Now, this R or the resistance is equal to rho L upon A, or whatever object you are. So rho is the resistivity of whatever object that you are using. Okay, and L is the length and A is the cross-sectional area. Next, conductance. The ability of a material to conduct electricity is known as conductance. It is just opposite of resistance. Okay, and as the temperature increases, the resistance increases, and so does the resistivity. Now, resistivity of an object does not depend upon the resistivity, this rho. This is only dependent on temperature, nothing else. Okay, and for different objects, this will be of different values. Next, for a resistor, if you would have seen a resistor, it is a small device like this with multiple colors given here. So the resistance of that device is calculated using these color codings. Okay. Now let's get back to capacitors. So in the same concept, using the same KVL and KCL, we do the mesh analysis and nodal analysis of it. Okay. Now, what is the energy stored inside a capacitor? That is calculated using 1 by 2 CV square. Okay. And instead of, so Q is equals to CV. So Q is equals to CV. So instead of this half CV square, we can use whatever values is given to us in alternating equations like this. Okay. Now time constant. Time constant tau is equals to RC. So RC is when you have a RC circuit given to you. After 1 tau time, the capacitor gets 63% charge. So that is the time constant about it. Okay. Now, capacity of a capacitor, C is equals to Q upon V. C is positive constant, and for a conductor, and it is called capacity of a capacitor. Okay, this we already covered. Next, electrostatic force between plates of a parallel plate capacitor. So if you have a parallel plate capacitor, the net energy is E0 minus En. Okay. Next, we have the dielectric, or whatever is the medium kept between the two capacitors. Okay. So dielectric inside the capacitor, E epsilon naught upon K. That is C into K epsilon naught. If there is no dielectric, that is just epsilon. Moving forward, charging of a capacitor. This is the formula for charging of a capacitor, Ce into 1 minus I upon e to the power 1 minus Rc. Okay. And as the time increases, the charge, it follows a parabolic curve like that. Okay. Now, current at t is equals to 0 and t is equals to infinity. Now, if t is equals to 0, if you put it here in the equation, in the second one. If t is equals to 0, then what? E to the power 0 will be 1. So, E upon R. So, at time, so this is your calculation for current and your electric charge. Alright. Now, moving forward is your electromagnetic induction. Now, electromagnetic induction happens because there is, due to the change in magnetic field, a current is induced in a circuit. Okay. So when we talk about electromagnetic induction, one of the most important thing is change in the magnetic flux with respect to time produces a voltage, produces a EMF. Okay. This is the first concept. Now, next, this flux is equals to BLV. Okay. And whatever is the amount of induced EMF, that is flux into the change in flux into the value of B. B is the magnetic field. Okay. Now, self-inductance is when an object, when the change in flux of an object induces EMF in itself. Okay, that is called as self-inductance. And energy stored in an inductor is equals to minus L di by dt, and L is the inductance. Okay. EMF induced is d into F or di into dt. Okay. Next, we have mutual inductance. When the induced current happens because of change in flux of the first coil, a current is induced in the second coil, that is called as induced EMF. Okay, or mutual inductance. Because the coil in which current is getting induced here in mutual inductance is not the same one in which there is change. Okay, so M2 upon 1. And EMF in this case is equals to what? Minus M d phi upon dt. Alright. Now, next we have the Lenz's law. Now, what does the Lenz's law says? So, first by Faraday's law, we found out that whenever there is a change in flux, because of change in flux, an EMF or a voltage is induced. Now, what will be the direction of voltage is told by the Lenz's law. So, what does Lenz's law works on the conservation of? So, yeah, so conservation law, okay. So, what Lenz's law tries to explain is if there is a change in flux, because of that change in flux, what happens is if the flux is reducing, the induced EMF is such that it increases the magnetic flow. Okay, so that is what talks about Lenz's law. Now, moving forward, energy stored inside an inductor, that is equals to EL di by dt, like we discussed before, right? Now, so in that case, we have the series combination and the parallel combination again of an inductor as well. Here, as we can see, L1 and L2 are connected in series, and here this L1 and this L and H are connected in parallel. Okay, and the addition in series combination they are just added normally, L1 plus L2 plus L3. In parallel, they are added 1 by L1 plus 1 by L2 is equals to L equivalent. Okay. Now moving forward, next we have the waves. Maxwell gave a concise equation of all these previously seen laws. Okay, first he gave, as we discussed about Gauss law, E into for a closed surface, E dot dA is equals to Q upon epsilon naught. Okay, then for magnetism, he saw B dot dA is equals to 0. That is Gauss law for magnetism. Next, by Faraday's law, E dot dl is equals to d phi by dt, change in flux with respect to time. Okay, and then we have Ampere's Maxwell law. So B dot dl will be equal to mu naught I plus mu naught E. So in Ampere's Maxwell law talked about electromagnetic as well as current and electromagnetism. Okay, so mu naught I plus mu naught into mu naught E into d phi dE by dt. Now, where mu naught is the permittivity constant of the free space, and epsilon naught is the permittivity of the free space, and mu is the permittivity of the medium, and epsilon naught is the electric permittivity of the medium. Okay, now moving on, we have displacement current. Now, Ampere's Maxwell law gives for B dot dl, mu is equals to IC plus ID. IC is the current that is passing through the polarized format here, and D is the displacement current. Okay, now when we talk about electromagnetic wave, these are waves that have both electric and magnetic field, and they make an angle of 90 degrees with each other. Okay, and one more thing mentioned here, this is magnetic, one second, this is magnetic permittivity and this is electric permittivity. Okay, all right. Now moving forward, EM waves. So what EM waves are? They are electromagnetic waves which has both electric field as well as magnetic field, and they are moving. They are perpendicular to each other, and the direction of the waves is moving in the third direction. Okay, so we have E in Y plane, V in Z plane, and the wave is moving in X direction. Okay, now electromagnetic waves can be polarized. What does a polarized waves means? See, waves can be of, wave can look like this. Okay, but if we have a polarizer, what it does is it polarizes the wave so that only one single phase of wave passes through the surface. Okay, next we have energy density of the waves, that is 1 by E epsilon naught upon E square RMS, or B square RMS upon 2 mu naught. And total energy density, same formula, E naught upon E square RMS, or B naught B square RMS upon mu naught. Okay, next, visible spectrum. So see, light waves or waves in general have a lot of range. They can range from long radio waves that ranges from 10 to the power 0 in the range of 10 to gamma waves that are ranging from 10 to the power 24, that are high frequency. This range is the frequency. Okay, so long radio waves, they have the very low frequency. Okay, and high frequency rays, that is gamma rays, that have power ranging from 10 to the power 24. Now, from that, a very small spectrum is there that are visible to us. That is the visible spectrum. Okay, and beyond that, we have infrared, ultraviolet, microwaves, X-ray, gamma ray, short radio waves, and long radio waves. So, long radio waves are what? Wavelengths, waves which have wavelength less than 0.1 meter. Okay, we use it in radios, television, communication, etc. Then we have microwaves that are used in radar system, ovens, etc. We have infrared that are used in household remotes. Then we have visible rays that we are actually able to see. That range is only from 700 nanometers to 400 nanometers. Then we have ultraviolet rays that are used for water purification, eye surgery, and X-ray that are used for medical diagnostic. And gamma rays are used to destroy cancer cells. Okay. Now, moving forward, we already discussed the current section. But okay. Now here we have the Biot-Savart law and the magnetic field. Okay. Now, what does Biot-Savart law means? States. So, let's say if there is a current carrying conductor, okay. So, if there is a current carrying conductor and it will have a magnetic effect because of that. So, the magnetic field due to a current carrying conductor will be is proportional to the length of the conductor, the distance at which we are calculating it. So, the formula is mu naught by 4 pi I dl cross r upon r cube, and the SI unit of magnetic field is Tesla. Okay. Now, magnetic field intensity due to a straight current carrying wire, the similar formula that you have seen in electrostatics as well, mu naught I upon 4 pi r sine theta plus cos theta. Okay. Now, if we have a center, at the center of a current carrying loop, if you have to calculate, that is mu naught I upon 2r. Center of a current carrying circular loop, mu naught I alpha into 2r upon 2 pi. And at axis of a current carrying loop, at some distance here, this is the formula for it. Magnetic field intensity due to a current carrying wire of a hollow cylinder. These are the multiple scenarios that you can go across once. Next, we have a solenoid. So, if we have a solenoid, that is a spring-like structure that is wrapped around some insulating medium. So, in that case, the magnetic field due to a solenoid is mu naught Ni upon 2 sine theta 1 plus sine theta 2. Okay. Now, next we have magnetic field due to a current carrying loop that we already saw. This is how the graph or the image of it will look like if we draw imaginary magnetic field lines around it. Next, we have a toroid. Toroid is a circular object like this, around which the current carrying conductor is wrapped. So, magnetic field due to a toroid is mu naught Ni, and magnetic moment, that is equals to Nia. Okay. Now, if we have a current carrying loop, the torque due to a current carrying loop is mu naught mu cross B, or this is the dipole and this cross B. Okay. Then magnetic moment due to rotation of charge. If charge is rotating, because of that, the magnetic moment is Q upon 2m. Now, next we have the Ampere circuital law. Now, what does that state? If we do the line integration across a closed surface, that and to calculate the magnetic field around the line integral of it, that is equals to mu naught times whatever amount of current is enclosed by the surface. Okay. Next, we have the properties of magnetic field lines. So, these are straight current carrying wire. In case of straight current carrying wires, magnetic field lines are circular with their center on the wire. Okay. Then, so it looks like something like this. Tangent to magnetic field lines at any given point gives the net magnetic field at that point. Okay. And magnetic field lines forms continuous closed loops. Now, moving forward, magnetic force due to a moving charge. If there is a charge moving inside a magnetic field, the force experienced by it will be Q into V cross B. Okay. Now, a motion of particles in a plane, in plane to B. So, like we saw, it will try to move in a circular object, and if something is moving in circular radius, what will happen? There will be a if something is moving in circular radius, there will be a centripetal force that will be mv square upon r. Okay. Next, we have a cyclotron. Now, cyclotron is a device that we use to give high speed to charged particles. Okay. So, this frequency of the charged particle once it will leave the cyclotron will be qb upon 2 pi m, and this t is 2 pi m upon qb time period while moving through this whole circle. Okay. Next, to calculate the direction of magnetic field, what we do is we hold the right hand. From our right hand, we hold the wire in which the current is carrying, and we point the thumb towards the direction of current, and the curling fingers of our thumb, that gives you the direction of motion. Okay, or direction of magnetic field. Now, motion of charged particle in presence of both E and B. So see, if there is electric field, that is QE, and because of magnetic field, that will be Q into V cross P, correct? Now, when the wires are perpendicular to each other, the forces, if we have two current carrying wires, in that case, the force between them is calculated using this formula. Moving coil galvanometer, in that, the tau will be NIA into V, okay? A is the area, B is the magnetic field, I is the current. Now, magnetic field or a current carrying wire kept in a magnetic field. If we have a current carrying wire which is kept in a magnetic field, the force experiences IDL cross V, okay? And this is the same formula as we saw before. But here, these two wires are parallel to each other, and okay, in this case, these were perpendicular to each other, right? Okay. Now, moving on, we have alternating current. So, when we talk about alternating current, the source voltage of the current that we are getting is of a sinusoidal nature. Okay. So, voltage increases and decreases. So whenever we talk about alternating current, voltage or any average voltage or RMS voltage is always calculated across half wave, right? Because if we take a full wave, it will turn out to be 0. Now, we have two major things here, root mean square voltage of voltage or root mean square current, and average voltage or average current. Now, RMS value of voltage will be RV peak, or the maximum voltage, divided by under root 2. That is how we calculate RMS voltage. And average voltage is equal to 2V max upon pi. Okay, that is only for half range of current. Now, moving forward, in alternating current, we discuss three types of circuit. VLR circuit, R circuit. So we have three components that we have till now come across: resistor, capacitor, and inductor. So we take into account all three of it. So in a pure resistive circuit, the voltage is V naught sine omega t, and current and voltage are on the same phase. So it becomes I naught sine omega t. Okay. The resistance here is only applicable because of R, and the cos phi is VR by VC. So that is about a pure resistive circuit. Okay. Then we have a pure capacitive circuit. Here we write it as C. In this case, voltage is equals to V naught sine omega t, and current I. The current will have I. Okay, and it will be I naught sine omega t plus pi by 2. In case of a pure reactive circuit, in pure capacitive circuit, voltage runs by a phase of 90 degree before current. Okay, so there is a phase difference between current and voltage, and current has a phase of 90 degree higher than the voltage. All right, and I is equals to VC upon R, the same concept, and R will be the capacitive reactance of the circuit. So as you can see here, V is equals to V naught sine omega t, and I is equals to I naught sine omega t plus pi by 2. Okay, and the reactance or the resistance in this case will be due to the capacitor. So that will be capacitive reactance, right? Then we have a pure inductive circuit. Again, in this case, voltage runs before current by an angle of 90 degree. So the voltage will be V naught sine omega t, and current will be I naught sine omega t minus pi by 2. Okay. Now, and in this case, the whatever resistance is offered is only coming because of the inductive reactance. So that is the resistance of the circuit. Then we have LR circuit. There is a inductor and a resistor. Okay. So the voltage is equals to V sine omega t, and current will be calculated by depending upon the capacitance. So now in this case, capacitance will be R square plus L omega square upon R. Okay. We take the inductive reactance and the normal resistance into count. Then in the case of an RC circuit, we have a capacitor and a resistor. So in that case, the average resistance that is offered is because of the resistance plus omega square upon L. Okay, that is the capacitive reactance. Next, and the performance in LCR circuit looks like this. This forms a bell-like structure. Then we have transformers. Now, transformers are used to change the amount of voltage when we move from one coil to another. So, let's say in this primary coil, the voltage is Vp, and there are n number of turns in this. And in the secondary point, we want to reduce or increase the amount of voltage. So, here we have that will be the secondary coil voltage Vs, and there are n number of turns in this coil. So, Vs by Vp is equals to Ns by Np. Ns is the number of turns in the primary coil, and secondary coil, and Np is the number of turns in the primary coil. Okay. Now, the power remains same in the both the coils. So voltage in VI in the primary circuit will be equal to VI in the secondary circuit. Okay. Now, if the number of turns in the secondary coil is greater than the number of turns in primary coil, this is called a step-up transformer. Okay. And the same, if the number of coils in the primary coil is greater, this is called a step-down transformer. Because why a step-up transformer? Because that will give an increased voltage. Okay. Now, when we're talking about normal transformer, we assume an ideal case where there is no loss in the flux. Okay. Now, in an actual transformer, what happens? Due to the flux linkage, due to the pure design, the air gaps are there. Okay. So in actual transformers, there is some energy loss takes place. Okay. So what we can do to rectify this air gaps thing, we wind it by primary and secondary coil one over the another. Okay. So there is no air gaps present. Then resistance of winding causes heat loss. So in high current, low voltage winding, these are minimized by using thick wires so that there is no heat loss. Eddy current, what is eddy current? Eddy current, it happens because the large sheets, they gain current in itself. So that can be reduced using the laminated cores. And then there's hysteresis loss. That can be minimized using magnetic material having low hysteresis loss. Okay. Now, then we have an LC oscillation. Now in LC oscillation, there is no resistor here. And the whatever charge is being supplied, let's say there is a charged a capacitor placed here. Now what will happen? The charged capacitor, once it is linked to the circuit, it will start flowing current, and that current is starts getting stored in the inductor. Once the inductor gets completely charged, it starts flowing current, and that charge starts getting stored in the capacitor. So these oscillation between charge from inductor to capacitor and capacitor to inductor keeps happening, and this is known as the LC oscillation. This also behaves like a spring balance. Okay. Now, a spring block. So what is being constantly transferring here? The charge that is constantly moving, and in case of spring, the distance keeps on increasing and reducing. What is the flow? The I is equivalent to velocity, and the 1 by C is equivalent to the K constant, and L is the mass. Okay. Now, similarly, the potential energy of this LC oscillation is Q square upon 2C. Similar to the potential energy of a spring, that is 1 by 2 Kx square. Magnetic energy is 1 by 2 Li square. Kinetic energy is 1 by 2 mv square. So this is how you can relate between the two concepts, okay, and how this behaves as a spring law. All right, let's get started with modern physics now. So, according to Rutherford's gold foil experiment, most of the particles nearly went 99% through the surface, and only few of them got deflected. So that showed that electrons' positive charge is centered towards the center, and the rest of the part is hollow, and electrons revolve around it. Now, distance of a closest approach for a particle is r is equals to k z e to the power 3 square into k. Okay, z is the atomic number of the particle. Now, energy during transition. So whenever we are shifting a particle from one stage to another, or one circle to another, or one shell to another. So the energy is final stage versus minus the initial stage. So the formula is 13.6 and divided by 1 by n1 square minus 1 by nf square into the atomic number. All right. Now for hydrogen element, in the different excitation stage, in the ground state, this is the voltage of the particle, and as we keep shifting to the upper stages, the amount of energy required to shift it out from for the electron to jump out of the shell is as follows. Okay. Next we have hydrogen line spectrums. So jumping of particle from different shells as it goes down from 7th to 6th to 5th to 4th have been named under different categories. We have the Balmer series, we have the infrared series, and so on. All right. In the Bohr's model, electrons were revolving only around the orbits whose angular momentum was given by this mvr, okay, and is an integral multiple of h upon 2 pi, okay, and this is the formula, mvr is equals to nh upon 2 pi. Now, what is the radius of a Bohr's orbit as given? So the radius of the Bohr's orbit is given by this formula, and the easier to remember one will be 0.529 into n square upon z. This is the radius of each cell or each orbit, okay. Energy of an electron, that is the kinetic energy, and that is equal to half the potential energy, and this is the energy of the electron, 13.6 into 10 to the power z square, that is the atomic number divided by n number, that's shell number, okay. And r here is the Rydberg's constant. The value of the Rydberg's constant is 1.1 10 to the power 7. Now, velocity of electrons, or what is the velocity in which it is revolving in different shells, is given by this formula. Now, the number of emission lines that will be formed when the electron jumps from first some N1 cell to some N2 cell is calculated using this formula. Okay. Now, moving forward, next is the de Broglie's wavelength. De Broglie's wavelength is calculated using just this formula: lambda p is equals to h. Okay, or we can also calculate h and p is the momentum, so under root 2m ke can also be used to calculate the same. All right. Now, the graph between the voltage in N and the threshold frequency is denoted using this. Threshold frequency is the minimum amount of frequency required for the electron to jump from the shell. Okay. Then we have the saturation current. Now, the maximum value of the photoelectric current that can be attained is known as the saturation current. This is the IS or Imax. Okay. Stopping potential. The value at which the photocurrent just stops is called the stopping potential of the current. Okay, and that is also equal to the maximum kinetic energy of the electron. Next, we have the threshold wavelength, maximum wavelength of E for so the electron just jumps out of its threshold wavelength. Okay, and to calculate it, you use this formula hc upon lambda or minus 1 upon lambda naught. Lambda naught is the threshold wavelength. Okay. Now, the threshold frequency, again same formula, k is equals to hv minus hv naught. V naught is the threshold frequency. So, the minimum frequency for which electron just comes out is called as the threshold frequency. Alright. And here we have different graphs showing the same concepts. Moving forward, radius of a nucleus. Now, for each nucleus, the A is the atomic number and the radius is denoted using this formula. Density of the nucleus, that will be mass per unit volume. You can calculate it just basically like this. Next is the nuclear force theory. It is the theory that suggests how the nuclear force is the force which holds the nucleons inside it together and how stable it is. Now, for atomic number less than 20, it is a more stable. Okay, nuclei have N:2p ratio nearly 1:1. Neutrons and photons are equal in nature. As we start going ahead, that ratio increases to 1 to 1.5. Okay. Now, for atomic number greater than 83, we don't have a very stable nuclei. Okay. Then we have the mass defect. The difference between the mass of the constituent nucleons and the nucleus is called as the mass defect. Okay. And you can calculate it, delta m is equals to m1 plus m2 minus m3. M3 is the mass difference. Okay. Now, moving forward. If A plus B is equals to C plus D plus energy, and the A and B are the reactants, and C and D is the product, then the gain in energy is the Q value. Okay. So, if the BE product or the energy of the product is greater than the energy of the reactant, then the energy will be released. Okay. That will be an exothermic reaction. Next is the binding energy of nucleus. Now, binding energy of nucleus is the energy released when the constituent nucleus are brought from infinity to form a nucleus. When the constituent nucleons, so that when we add the protons and the neutrons into the nucleus, the amount of energy needed to form that is known as the binding energy of the nucleus. Okay, and the formula is Be upon number of nucleus. Mass and energy of a particle is equivalent to energy CE. E is equals to mc square is one of the most prominent equations that you will come across. Okay, and this is also known as rest mass energy formula. Now, atomic mass unit AMU is the 1 upon mass of carbon minus 12 atoms. That's about it. Okay. Now, moving forward, radioactivity. So, whenever there is an unstable nuclei, it starts losing particles. Okay, the number of nuclei decay across the course of time is known as the law of radioactivity. Okay, then we have nuclear fusion. So, if you have a uranium atom of uranium-235, okay, and you add an extra neutron to it, we have and other elements, we have the reaction here. Then we have the nuclear fusion, light nuclear fusion combined together in nuclear fusion reaction. Okay, energy is released in this more than the normal fission reaction. Now, how is the activity of decay reaction? That is denoted by dN by dt, when A is equals to n lambda. Okay, so we get A is equals to A naught upon 2t. Into 2t minus, this is the formula given to you. Now, the SI unit of decay is called Bakewell. Okay. Now, moving forward, we have the gamma decay. So, when we add gamma rays to any existing atom, to some existing atom, the gamma rays are deflected out of it. Okay. Then we have the K capture, and that is also given with this formula. Okay. And the mass that is lost through this is calculated using this. Now, moving forward, we have the half-life of mean or average life of any for any nucleus. That is the amount of time taken for half decay of the whole process. Okay, and that is easily calculated by ln upon lambda. Next, we also have alpha decay and beta decay. So you will get your helium atom here, and for any random atom, alpha decay means alpha particles are released out of it. Okay, Then we have the beta decay, or where the electrons with 0 mass and -1 charge is decayed out of it. Okay. Now moving forward, we have the X-ray spectrum. Now, what is continuous X-rays? Continuous X-rays are emitted due to high retardation of electrons coming from cathode. Okay. The minimum wavelength beyond which X-ray is emitted is called as the cutoff wavelength or the threshold wavelength. This is the formula for it. Next, what are the characteristics of X-rays? These are emitted when electrons from cathode are knocked out of an inner electron form to target material, and its position is filled by a higher energy level electrons. Okay, so these are the characteristics of X-ray. Now, moving forward, we have the Bragg's law that shows the number of constructive interference that will be formed because of these particles emission. Okay, and the formula is 2d sine theta upon is equals to n lambda. For constructive interference, we always require n lambda. Okay. Now moving forward, we have the next topic as SHM. Now, what is SHM? Simple harmonic motion. So whenever there is a to or flow motion or any continuous motion that is harmonic or being repeated at the same frequency, it is known as an SHM. Now, when we talk about SHM, the first thing that should be coming to our mind is a spring block system. Now, in a spring block system, the internal energy is half kx square and the kinetic energy is 1 by 2 ka. A is the amplitude or the maximum displacement minus x square, right? So, kinetic energy plus internal energy gives the total energy of the system, that is always constant, okay? That is 1 by 2 ka square. Now, moving on, we have the spring block system. When you come, so each spring block will have a spring constant k. If you have two springs attached in parallel, the k equivalent becomes k1 plus k2. If they are attached in series, the k equivalent is also calculated in the same way, that is 1 by k1 plus 1 by k2. So k1 k2 comes up and k1 k2 multiple comes up and k1 plus k2 is below. Now the time period of the SHM is always 2 pi m upon k equivalent. So for normal case it will be just k, and as we move ahead. Next, we have a torsional pendulum. Now, what is a torsional pendulum? So, torsional pendulum is a pendulum where there is a disc attached at the base. So, in this case, the time period is 2 pi I upon c. I is the inertia of the pendulum across the midpoint. Okay. Now, moving forward, then we have a physical pendulum. In the physical pendulum, the pendulum keeps we have a structure. Okay. That structure moves like a pendulum. In that case, also the time period is 2 pi. Inertia, that is I, divided by mgd. M is the mass of the object and d is the distance, okay, between the center of mass and the hinge from where the pendulum is oscillating. Now, moving forward, so when we have an SHM, in that case, when the phi is 0, y is equals to a1 plus by a2 into x. When the phi is pi, it is minus a1 by a2 into x. And so these are different values for which different kinds of shape will be formed. Now, next is velocity analysis. So normally when a SHM is happening, the equation for SHM is a sine omega t plus phi. Velocity will be just the differentiation of it. So dx by dt, that is a omega cos omega t plus phi, right? Now velocity and displacement are in the same direction, but if you differentiate it again, the acceleration or the retarding force is always in opposite direction. The force, that is this force constant, this kx, that force always tries to bring the SHM back to its default or mean state. Okay. Now moving forward, we have a damped oscillation or damped SHM. Now what does damped SHM mean? So when we talk about SHM, we're talking about an ideal case. But in normal scenario, when you compress a spring, it oscillates for some time, and after a point, this SHM will stop because of friction, because of the damping in the environment. So whatever reasons can it be, but the SHM after a fixed period of time will stop. So that is known as a damped SHM, and these are the formulas for it. Now, similarly, if we just artificially or superficially force it to always be moving in a continuous motion, that will be called as a force oscillation. Okay. Moving forward, next we have sound waves. So, what are sound waves? Now, so when we have sound waves and we are they are longitudinal waves, right? Now, so variation of excess pressure in gas due to propagation of waves. So when there is a gas and there is propagation of longitudinal waves, the excess pressure is minus b ds by dx. What is ds? ds is the propagation wave. Okay. Now, moving forward, the power transmission in sound waves. So as because of the sound wave, there will be some power transmission happening, and that is equals to 1 by 2 under root b rho sine s square omega square. And s square omega square are the property of the source, and b and rho are the property of the medium in which the transmission is happening. Now, Moving forward, characteristics of sound waves. So we have pitch. Now, what is the pitch? Are two types. There is a high pitch sound and there is a low pitch sound. Okay, or a high frequency or low frequency sound. So a low frequency sound means that the number of waves happening per second is low, whereas in a high frequency sound, number of waves being covered per second is high. Now, next we have the loudness. Next we have the quality. How smooth is the transition between the waves? That is a good or bad quality sound. If the transitioning is not smooth, it is a bad quality sound. Okay. Next we have the loudness, or whatever is the maximum amplitude of the sound. Okay, that is denoted using decibels. Okay. Now, moving forward. Variation of intensity. Now, if it is starting from here, the intensity of the sound wave as you start going further and further gets reduced. And the formula for intensity is P upon 4 pi r square. Okay. Now, power per unit length. This is again the same thing. That is again intensity PL into 2 pi RL. This is for a cylindrical system. Now, equation of sound waves. Now, how do we denote a sound wave? That is denoted by S naught sine omega t kx and phi. S is the displacement of particles, right? Omega is the angular frequency and x is the displacement and phi is the phase in which the sound is being transmitted. Now, if we talk about different types of gases, the velocity of sound waves varies, right? So it depends upon the gamma also, the pressure and the rho or the density. Okay, if P and T is constant, the velocity will not change. Now, moving forward, resonance tube method to calculate speed of a sound wave. So you must have seen the resonance tube and how the first resonance, second resonance, I hope all that part is clear to you. So using those resonance, we calculate the velocity of sound wave V is equals to F lambda. Okay. Now, next is wavefront. Wavefront, just like in the normal waves. So when we project one wave to the second, when we project all the lines of a single first wave to construct a secondary wave, that is called as a wavefront. Okay. Now, change in wavelength due to motion of a sound. So, if the velocity, if the person who is listening and the person from where the source of sound is coming, both are in motion. In that case, there is a change of wavelength, okay, as it travels, and that change is equals to this velocity of the source, velocity of the viewpoint, and f. Okay. Now, moving forward, interference of sound waves. So, if there are two sound waves having different frequencies, this is the formula of interference. And the superposition principles is also applied here. So if there are two sound waves, they will be superimposing each other. The amplitude of both the sound waves will be squared and the angle will be, by taking the angle, we take cos theta. Okay. Now, similarly, we also have constructive interference and destructive interference in sound waves as well. So for constructive interference, it should the interference should be in the 0, lambda, 2 lambda, 3 lambda, and n lambda format. Okay. But for destructive interference, it should be n plus 1 by 2 lambda. Okay. Next, we have the standing waves, or the waves which are while transmission they are maintaining a constant fundamental shape. Okay, that is the standing waves. Now, in standing waves, the fundamental node, it is n lambda by 2 is equals to n. That is the first one. Now, the first overtone, the third overtone, this is how we go with harmonics, overtones, and all that. Okay, so the first overtone will be having how much? The first overtone will be having one whole wave and a half of it. Okay, so that is the first overtone or third harmonic. Now, if we talk about an organ pipe, if it is closed on one end, that side is taken as the node. If it is open, that side is taken as the antinode. Okay. So now, if we're talking about standing wave in an open organ pipe, so if this side is open, this will be an antinode and this will be a node. And the wavelength here is lambda by 4, and the amount of length of the wave covered is lambda by 4. That will be equal to L. So frequency is V upon 4 lambda. That is the fundamental frequency. Then we'll have the first overtone where we have one antinode here. Then we'll have the second overtone where we have two antinodes here, two notes here. So like that we proceed forward. Okay, and that the first overtone forms the third harmonic or the fifth harmonic. So the harmonic is dependent upon this. Okay, whether it will be the first or second or third. Now, inside a closed organ pipe, both ends are nodes, and between it is the antinode. So this is half of a wave. So lambda by 2 is equals to L. So F naught, or the fundamental frequency, becomes V upon 2L. Okay. Now, in case of first overtone, there will be instead of having one single antinode, we'll have two antinodes. In the case of third harmonic, we'll be having 3 antinodes, and so on as we move ahead. Okay. And in this case, the second harmonic is first overtone, because see, this is the value is 2 here. Okay. Now, moving forward, next we have waves on a string. moving forward, we have waves on a string. Now, let's get started on that. So, whenever we're talking about waves on a string, that means one end, we have a string and either one end or both the ends are fixed, right? So, power transmission when traveling on a wave. So, this will be for all waves. Okay, the same concept as we saw for the sound waves. Now, and where the T is the tension in the string and mu is the medium in which it is traveling, and A and omega is the amplitude and the angular velocity or the wave phase length. Now, moving forward, general equation of sound waves, that is A sine kx plus omega phi and sine omega t phi 2. Okay, if we have talking about a standing wave. Now, moving forward, amplitude component of the wave is A. Okay, and the coefficient of x is k. Wavelength component of the wave is 2 pi upon k, and the loop length or the length of each wave here is lambda by 2. Okay, now velocity of a wave when it is traveling on the string, that will be equals to t upon mu. Okay, mu is the mass per unit length, as also mentioned here. Okay, now moving forward, next we have the interference of a wave. So for interference, as we discussed before, the to perform two types of interference happens, constructive and destructive, right? So for constructive interference of the waves to happen, the phase difference should the phase ratio should be n pi, and for destructive interference it should be n plus 1 by 2 pi. Okay, now moving forward, so waves are of two types, mechanical waves and non-mechanical waves. So now non-mechanical waves do not need a medium to travel, right? For example, we have light waves. Next, mechanical waves, they require a medium to travel on. Okay, so for example, sound waves. Now in mechanical wave, again we have two types, longitudinal waves and transverse wave. Now what are longitudinal waves? These are the waves that in which the oscillation medium is along the direction of the wave's propagation. So for what does that mean? If these are the particles of the wave, they are vibrating in the same axis as the direction of wave's propagation. Now in transverse wave, that is example of waves on the string. Here what we can see, the wave is traveling in up, the particles of the wave are traveling up and down, whereas the motion of the wave is in forward direction. So the direction of propagation of wave is perpendicular to the motion of particles. So that is the transverse wave. Okay. Now, when we write wave function, it is that is denoted by x and t. X is the transmission and t is the time. We can write it as a sine kx minus omega t, similar to whatever we have seen in the case of SHM as well. Okay. Now, a sinusoidal wave equation is written like this: a sine omega t minus kx plus phi, where phi is the phase difference. Okay, and lambda is equals to 2 pi upon k, and the time period is 2 pi upon omega, right? Then angular wave number, that is k, is equals to 2 pi upon lambda. Now velocity of acceleration of particle, you just differentiate the y to get velocity and differentiate the velocity to get the acceleration. Okay. Now that is omega square minus y minus omega square y. Okay. Now moving forward, we have the standing waves. So as we discussed about the organ pipes. Now when we talk about standing waves, so when we talk about a standing wave, the equation is again 2a sine kx cos omega t. Okay. Now so like we discussed about the organ pipes, right, as I was explaining. So in organ pipes we have the standing waves present there, right? So similarly, similar to that, the normal modes of a string. So if in the organ pipe, like we discussed, if the organ pipe is closed, that forms an antinode, and if the organ pipe is open, if the organ pipe is closed, that forms a node, and if it is open, it forms an antinode, right? Now similar to that, when the string is fixed, that side will not be moving, so that forms a node, and the string, the side which is not fixed, forms an antinode. So now we are talking about a normal mode string fixed at both ends. If both ends are fixed, both ends will always be forming nodes, right? Now, so if the length is this forms half a wave, so lambda by 2 will be equal to L, right? Because a full wave will be lambda. So the first fundamental frequency will be n lambda. So in this case, the first fundamental frequency will be v upon 2L, right? Then again, if we have two antinodes, it will be the first overtune. Now the first overtune will be having one complete wave. That will be f is equals to 2v upon 2L, right? So that will be a second harmonic. Moving forward, for the third harmonic, you will have 1.5 wave here being formed. So 3 lambda by 2 is equals to L. So f is equals to 3v upon 2L. So that will be second overtone or third harmonic. Okay. Now, when the string is fixed only on one end, the other end will be forming antinodes, like I just explained. And so similarly, this will be forming only 1/4 of a wave. So lambda by 4 is equals to L. So the fundamental frequency will be V upon 4L. Okay. Now, again, when we'll be having when we'll be having the first overtune, that will be having two antinodes. So the frequency will be 3V upon 4L. That will be as again third harmonic, and so on as we continue on. So that next we have the concepts of wave optics. Now, till now we have already covered constructive interference, destructive interference. The next part is if the two sources are set, two sources of lights are there. Okay. So normally when we talked about ray optics, we were considering lights to be traveling in a straight path, like having they are just rays. Now, when we found out that the light bends across edges or they have a wave format, instead of particle nature, they are wave nature. They also have wave nature. So that gave rise to different concepts like we have superimposition, interference, and various other concepts. Now, two sources of light are said to be coherent if they produce waves having a constant phase difference. So the difference between the phase between both the lights should always be constant. Not that they should be having same phase, but the difference between phase should be constant. Okay. Now, two independent ordinary sources like lamps are incoherent in nature. Now, moving on, till now we have discussed constructive interference requires n lambda, right? So now, for constructive interference to occur, the cos phi should be equal to 1, right? So the phi can only be equal to 2n pi. Now, if there are two waves A1 and A2, two waves having amplitude A1 and A2, the maximum amplitude will become A1 plus A2. The intensity will be under root I1 plus I2 the whole square. Okay. Now for destructive interference, the cos phi value is -1. Now, so the phi can be 2n plus 1 pi. Okay. And in destructive interference, the amplitude is minimum. Okay. So A1 minus A2 is the amplitude. And intensity also is minimum in nature. Now, next is fringe widths. So what happens when we have two coherent source of lights, and they are they interfere, and on a plane you'll see fringes being formed like this. Now the width of the fringe, or that fringe width, is the distance between the first maxima and the first minima. Okay, so that is the distance, that is the width of the fringe. Okay, now that is equals to lambda d upon small d. D is the distance from the source to this plane or to the screen, and d is the distance between these two source lights. Okay, small d is the distance between these two source lines. Now, moving on. So again, when you have a variation of intensity, then the intensity is also 4i cos square phi by 2. All right. Next, moving forward, in the Young's double slit experiment, the same. This is the result of the Young's double slit experiment itself. Okay. In this case, the delta x is equals to y d upon capital D. D is the distance between the slit, and d is the distance between the slit and the screen. Okay, now moving forward, interference and reflection. So when we're having a reflection being formed, in that case, the interference, the constructive and destructive interference are formed like this: n lambda and n plus 1 lambda by n plus 1 by 2 lambda, and one forms the constructive interference, and n lambda forms the destructive interference. Now, when we talk about transmission, in that case, the interference structures are formed like this. Now, moving forward, the more important topic will be the Young's single slit experiment. Now, in single slit experiment, what happens? The first fringe that is formed at the center, that is of the greater intensity and of the higher length, higher width. Okay, and as we move forward, the intensity and the width of the fringe keeps on decreasing. All right. Now, next is the resolution of an optical instrument. So, just for a lens, the resolution or the ability to see apart two different objects is 1.22 lambda upon d. Lambda is the wavelength of the light that is entering, and d is the distance. Okay. Now, moving forward, resolving power of a telescope, that is d upon 1.22 lambda. Again, d is the diameter of the objective length. Next, resolving power of a telescope, that is 1 by d minimum. Okay. Again, that d minimum is 1.22 lambda by sine. YDAC with white light. Now, with white light, what happens? Different color fringe will be formed. Why? Because white light has different wavelength, different colors are having different wavelength inside it. So in that case, the beta or the fringe width will be lambda t. The formula will remain the same, but you'll see first it will be violet, then indigo, then red, and so on. The whole different spectrum of the light will be splitting throughout. Okay. Next, variation in YDAC. Now, in case of In case if we shift the source light, in that case the fringe center also shifts. Okay. Now, moving forward, polarization by scattering unpolarized light. So what happens? Like we discussed before, an unpolarized wave looks like this. Okay. So we use a polarizer to actually intend all the waves in a single direction. Okay. So and that gives us a polarized set of lights. Now polarization by reflector. So if we are using a reflector, so by that tan IB is the angle at which the polarization is required is equals to mu. This is the Brewster's law. Okay. And with this, all your topics have been covered. I hope you guys are prepared well for your upcoming IMU-CET. And all the best, guys. Thank you. The PDF here will be attached below in the description box, so don't worry about it. All the best for your exams. Thank you, students.